Learning objectives. In this chapter, the user would learn the following in detail: network structures, distributed system structures, distributed file systems, distributed coordination. Design issues. Making the multiplicity of processors and storage devices transparent to the users has been a key challenge to many designers. Ideally, a distributed system should look to its users like a conventional centralized system. The user interface of a transparent distributed system should not distinguish between local and remote resources. That is, users should be able to access remote resources as though these resources were local, and the distributed system should be responsible for locating the resources and for arranging for the appropriate interaction. Another aspect of transparency is user mobility. It would be convenient to allow users to log into any machine in the system rather than forcing them to use a specific machine. A transparent distributed system facilitates user mobility by bringing over the user's environment, for example, home directory, to wherever he logs in. Still another issue is scalability, the capability of a system to adapt to increased service load. Systems have bounded resources and can become completely saturated under increased load. For example, with respect to a file system, saturation occurs either when a server's CPU runs at a high utilization rate or when disks are almost full. Scalability is a relative property, but it can be measured accurately. A scalable system reacts more gracefully to increased load than does a non-scalable one. First, its performance degrades more moderately, and second, its resources reach a saturated state later. Even perfect design cannot accommodate an ever-growing load. Adding new resources might solve the problem, but it might generate additional indirect load on other resources. For example, adding machines to a distributed system can clog the network and increase service loads. Even worse, expanding the system can call for expensive design modifications. A scalable system should have the potential to grow without these problems. In a distributed system, the ability to scale up gracefully is of special importance since expanding the network by adding new machines or interconnecting two networks is commonplace. In short, a scalable design should withstand high service load, accommodate growth of the user community, and enable simple integration of added resources. Scalability is related to fault tolerance, discussed earlier. A heavily loaded computer can become paralyzed and behave like a faulty component. Also, shifting the load from a faulty component to that component's backup can saturate the latter. Generally, having spare resources is essential for ensuring reliability as well as for handling peak loads gracefully. An inherent advantage of a distributed system is a potential for fault tolerance and scalability because of the multiplicity of resources. However, inappropriate design can obscure this potential. Fault tolerance and scalability considerations call for a design demonstrating distribution of control and data. Very large-scale distributed systems, to a great extent, are still only theoretical. No magic guidelines ensure the scalability of a system. It is easier to point out why current designs are not scalable. We next discuss several designs that pose problems and propose possible solutions, all in the context of scalability. One principle for designing very large-scale systems is that the service demand from any component of the system should be bounded by a constant that is independent of the number of nodes in the system. Any service mechanism whose load demand is proportional to the size of the system is destined to become clogged once the system grows beyond a certain size. Adding more resources will not alleviate such a problem. The capacity of this mechanism simply limits the growth of the system. Another principle concerns centralization. Central control schemes and central resources should not be used to build scalable and fault-tolerant systems. Examples of centralized entities are central authentication servers, central naming servers, and central file servers. The ideal alternative is the functionality symmetric configuration. That is, all the component machines have an equal role in the operation of the system, and hence each machine has some degree of autonomy. Practically, it is virtually impossible to comply with such a principle. For instance, incorporating disk-less machines violates functional symmetry since the workstations depend on a central disk. However, autonomy and symmetry are important goals to which we should aspire. Deciding on the process structure of the server is a major problem in the design of any service. Servers are supposed to operate efficiently in peak periods when hundreds of active clients need to be served simultaneously. A single process server is certainly not a good choice since whenever a request necessitates disk input-output, the whole service will be blocked. Assigning a process for each client is a better choice. However, the expense of frequent context switches between the processes must be considered. A related problem occurs because all the server processes need to share information. One of the best solutions for the server architecture is the use of lightweight processes or threads. We can think of a group of lightweight processes as multiple threads of control associated with some shared resources. Usually, a lightweight process is not bound to a particular client. Instead, it serves single requests of different clients. Scheduling of threads can be preemptive or non-preemptive. If threads are allowed to run to completion, non-preemptive, then their shared data do not need to be protected explicitly. Otherwise, some explicit locking mechanism must be used. Clearly, some form of lightweight process scheme is essential if servers are to be scalable. Distributed coordination. We described various mechanisms that allow processes to synchronize their actions. We also discussed a number of schemes to ensure the atomicity of a transaction that executes either in isolation or concurrently with other transactions. We described various methods that an operating system can use to deal with the deadlock problem. In this chapter, we examine how centralized synchronization mechanisms can be extended to a distributed environment. We also discuss methods for handling deadlocks in a distributed system. It includes the following: event ordering, mutual exclusion, atomicity, concurrency control, deadlock handling, election algorithms, reaching agreement. Tightly coupled systems. Same clock, usually shared memory. Communication is via this shared memory. Multiprocessors. Loosely coupled systems. Different clock. Use communication links. Distributed systems. Event ordering. In a centralized system, we can always determine the order in which two events occurred, since the system has a single common memory and clock. Many applications may require us to determine order. For example, in a resource allocation scheme, we specify that a resource can be used only after the resource has been granted. A distributed system, however, has no common memory and no common clock. Therefore, it is sometimes impossible to say which of the two events occurred first. The happened before relation is only a partial ordering of the events in distributed systems. Since the ability to define a total ordering is crucial in many applications, we present a distributed algorithm for extending the happened before relation to a consistent total ordering of all the events in the system. The happened before relation. Since we are considering only sequential processes, all events executed in a single process are totally ordered. Also, by the law of causality, a message can be received only after it has been sent. Therefore, we can define the happened before relation, denoted by the arrow sign, on a set of events as follows, assuming that sending and receiving a message constitutes an event. If A and B are events in the same process and A was executed before B, then A leads to B. If A is the event of sending a message by one process and B is the event of receiving that message by another process, then A leads to B. If A goes to B and B goes to C, then A goes to C. Since an event cannot happen before itself, the goes-to relation is an irreflexive partial ordering. If two events A and B are not related by the go-to relation, that is, A did not happen before B and B did not happen before A, then we say that these two events were executed concurrently. In this case, neither event can causally affect the other. If, however, A goes to B, then it is possible for event A to affect event B causally. A space-time diagram, such as that in figure below, can best illustrate the definitions of concurrency and happened before. The horizontal direction represents space, that is, different processes, and the vertical direction represents time. The labeled vertical lines denote processes or processors. The labeled dots denote events. A wavy line denotes a message sent from one process to another. Events are concurrent if and only if no path exists between them. For example, these are some of the events related by the happened before relation in figure. P1 leads to Q2, R0 leads to Q4, Q3 leads to R4, Pi leads to Q4 since Pi leads to Q2 and Q2 leads to Q4. These are some of the concurrent events in the system: Q0 and P2, R0 and Q3, R0 and P3, Q3 and P3. We cannot know which of two concurrent events, such as Q0 and Pi, happened first. However, since neither event can affect the other, there is no way for one of them to know whether the other has occurred yet. It is not important which happened first. It is important only that any processes that care about the order of two concurrent events agree on some order. Relative time for three concurrent processes. Implementation. To determine that an event A happened before an event B, we need either a common clock or a set of perfectly synchronized clocks. Since neither of these are available in a distributed system, we must define the happened before relation without the use of physical clocks. We associate with each system event a timestamp. We can then define the global ordering requirement for every pair of events A and B. If A leads to B, then the timestamp of A is less than the timestamp of B. Below we will see that the converse need not be true. How do we enforce the global ordering requirement in a distributed environment? We define within each process Pi a logical clock, LCI. The logical clock can be implemented as a simple counter incremented between any two successive events executed within a process. Since the logical clock has a monotonically increasing value, it assigns a unique number to every event, and if an event A occurs before event B in process Pi, then LCI A is less than LCI B. The timestamp for an event is the value of the logical clock for that event. This scheme ensures that for any two events in the same process, the global ordering requirement is met. Unfortunately, the scheme does not ensure that the global ordering requirement is met across processes. To illustrate the problem, consider two processes P1 and P2 that communicate with each other. Suppose that Pi sends a message to P1 event A with LC1A equals to 200 and P2 receives the message P2 event B with LC2B equaling 195. Because the processor for P2 is slower than the processor for P1, its logical clock ticks more slowly. This situation violates a requirement since A leads to B, but the timestamp of A is greater than the timestamp of B. To resolve this difficulty, we require a process to advance its logical clock when it receives a message whose timestamp is greater than the current value of its logical clock. In particular, if process P receives a message event B with timestamp F and LC2B, which is less than T, then it should advance its clock so that LC2B minus T plus 1. Thus, in our example, when P2 receives the message from Pi, it will advance its logical clock so that LC2B equals to 201. Finally, to realize a total ordering, we need only observe that with our timestamp ordering scheme, if the timestamps of two events, A and B, are the same, then the events are concurrent. In this case, we may use process identity numbers to break ties and to create a total ordering. Mutual exclusion. In this section, we present a number of different algorithms for implementing mutual exclusion in a distributed environment. We assume that the system consists of n processes, each of which resides at a different processor. To simplify our discussion, we assume that processes are numbered uniquely from 1 to n and that a one-to-one mapping exists between processes and processors, that is, each process has its own processor. Centralized approach. In a centralized approach to providing mutual exclusion, one of the processes in the system is chosen to coordinate the entry to the critical section. Each process that wants to invoke mutual exclusion sends a request message to the coordinator. When the process receives a reply message from the coordinator, it can proceed to enter its critical section. After exiting its critical section, the process sends a release message to the coordinator and proceeds with its execution. On receiving a request message, the coordinator checks to see whether some or other process is in its critical section. If no process is in its critical section, the coordinator immediately sends back a reply message. Otherwise, the request is queued. When the coordinator receives a release message, it removes one of the request messages from the queue in accordance with some scheduling algorithm and sends a reply message to the requesting process. It should be clear that this algorithm ensures mutual exclusion. In addition, if the scheduling policy within the coordinator is fair, such as first come first served (FCFS scheduling), no starvation can occur. This scheme requires 3 messages per critical section entry: a request, a reply, and a release. If the coordinator process fails, then a new process must take its place. We describe some algorithms for electing a unique new coordinator. Once a new coordinator has been elected, it must poll all the processes in the system to reconstruct its request queue. Once the queue has been constructed, the computation can resume. Fully distributed approach. If we want to distribute the decision-making across the entire system, then the solution is far more complicated. One approach described next uses an algorithm based on the event ordering scheme. When a process Pi wants to enter its critical section, it generates a new timestamp Ts and sends the message request PITS to all processes in the system, including itself. On receiving a request message, a process may reply immediately, that is, send a reply message back to PI, or it may defer sending a reply back because it is already in its critical section. For example, a process that has received a reply message from all other processes in the system can enter its critical section, queuing incoming requests and deferring them. After exiting its critical section, the process sends reply messages to all its deferred requests. The decision whether process PI replies immediately to a request PJTS message or defers its reply is based on three factors. If process P is in its critical section, then it defers its reply to P. If process P does not want to enter its critical section, then it sends a reply immediately to PJ. If process P wants to enter its critical section but has not yet entered it, then it compares its own request timestamp with the timestamp of the incoming request made by process PJ. If its own request timestamp is greater than that of the incoming request, then it sends a reply immediately to PJ. PJ asked first. Otherwise, the reply is deferred. This algorithm exhibits the following desirable behavior. Mutual exclusion is obtained. Freedom from deadlock is ensured. Freedom from starvation is ensured, since entry to the critical section is scheduled according to the timestamp ordering. The timestamp ordering ensures that processes are served in FCFS order. The number of messages per critical section entry is 2 into n-1. This number is the minimum number of required messages per critical section entry when processes act independently and concurrently. To illustrate how the algorithm functions, we consider a system consisting of processes P1, P2, and P3. Suppose that processes P1 and P3 want to enter their critical sections. Process P1 then sends a message request P1 timestamp equals 10 to processes P2 and P3, while process P3 sends a message request P3 timestamp equals 4 to processes P1 and P2. The timestamp 4 and 10 were obtained from the logical clocks. When process P2 receives these request messages, it replies immediately. When process P1 receives the request from process P3, it replies immediately, since the timestamp 10 on its own request message is greater than the timestamp 4 for process P3. When process P3 receives the request message from process P1, it defers its reply since the timestamp 4 on its request message is less than the timestamp 10 for the message from process P1. On receiving replies from both process P1 and process P2, process P3 can enter its critical section. After exiting its critical section, process P3 sends a reply to process P1, which can then enter its critical section. Because the scheme requires the participation of all the processes in the system, however, it has three undesirable consequences. The processes need to know the identity of all other processes in the system. When a new process joins the group of processes participating in the mutual exclusion algorithm, the following actions need to be taken. The process must receive the names of all the other processes in the group. The name of the new process must be distributed to all the other processes in the group. This task is not as trivial as it may seem, since some request and reply messages may be circulating in the system when the new process joins the group. If one process fails, then the entire scheme collapses. We can resolve this difficulty by continuously monitoring the state of all processes in the system. If one process fails, then all other processes are notified so that they will no longer send request messages to the failed process. When a process recovers, it must initiate the procedure that allows it to rejoin the group. Processes that have not entered their critical section must pause frequently to assure other processes that they intend to enter the critical section because of these difficulties. This protocol is best suited for small, stable sets of cooperating processes. Token passing approach. Another method of providing mutual exclusion is to circulate a token among the processes in the system. A token is a special type of message that is passed around the system. Possession of the token entitles the holder to enter the critical section. Since there is only a single token, only one process can be in its critical section at a time. We assume that the processes in the system are logically organized in a ring structure. The physical communication network need not be a ring. As long as the processes are connected to one another, it is possible to implement a logical ring. To implement mutual exclusion, we pass a token around the ring. When a process receives the token, it may enter its critical section keeping the token. After the process exits its critical section, the token is passed around again. If the process receiving the token does not want to enter its critical section, it passes the token to its neighbor. If the ring is unidirectional, freedom from starvation is ensured. The number of messages required to implement mutual exclusion may vary from one message per entry in the case of high contention, that is, every process wants to enter its critical section, to an infinite number of messages in the case of low contention, that is, no process wants to enter its critical section. Two types of failure must be considered. First, if the token is lost, an election must be called to generate a new token. Second, if a process fails, a new logical ring must be established. Atomicity. The concept of an atomic transaction is a program unit that must be executed atomically. That is, either all the operations associated with it are executed to completion or none are performed. When we are dealing with a distributed system, ensuring the atomicity of a transaction becomes much more complicated than in a centralized system. This difficulty occurs because several sites may be participating in the execution of a single transaction. The failure of one of these sites or the failure of a communication link connecting the sites may result in erroneous computations. Ensuring that the execution of transactions in the distributed system preserves atomicity is the function of the transaction coordinator. Each site has its own local transaction coordinator, which is responsible for coordinating the execution of all the transactions initiated at that site. For each transaction, the coordinator is responsible for the following: starting the execution of the transaction, breaking the transaction into a number of sub-transactions and distributing these sub-transactions to the appropriate sites for execution, coordinating the termination of the transaction, which may result in the transactions being committed at all sites or aborted at all sites. We assume that each local site maintains a log for recovery purposes. The two-phase commit protocol. For atomicity to be ensured, all the sites in which a transaction T has executed must agree on the final outcome of the execution. T must either commit at all sites or it must abort at all sites. To ensure this property, the transaction coordinator of T must execute a commit protocol. Among the simplest and most widely used commit protocols is the two-phase commit 2PC protocol. Let T be a transaction initiated at site SI and let the transaction coordinator at SI be CI. When T completes its execution, that is, when all the sites at which T has executed from CI that T has completed, then CI starts the 2PC protocol. Phase 1. CI adds the record prepare T to the log and forces the record onto stable storage. It then sends a prepare T message to all the sites at which T has executed. On receiving the message, the transaction manager at that site determines whether it is willing to commit its portion of T. If the answer is no, it adds a record no T to the log, and then it responds by sending an abort T message to CI. If the answer is yes, it adds a record ready T to the log and forces all the log records corresponding to T onto stable storage. The transaction manager then replies with a ready T message to CI. Phase 2. When CI has received responses to prepare T message from all the sites, or when a pre-specified interval of time has elapsed since the prepare T message was sent out, a CI can determine whether the transaction T can be committed or aborted. Transaction T can be committed if CI has received a ready T message from all the participating sites. Otherwise, transaction T must be aborted. Depending on the verdict, either a record commit T or a record abort T is added to the log and is forced onto stable storage. At this point, the fate of the transaction has been sealed. Following this, the coordinator sends either a commit T or an abort T message to all participating sites. When a site receives that message, it records the message in the log. A site at which T has executed can unconditionally abort T at any time prior to it sending the message ready T to the coordinator. The ready T message is, in effect, a promise by a site to follow the coordinator's order to commit T or to abort T. A site can make such a promise only when the needed information is stored in stable storage. Otherwise, if the site crashes after sending ready T, it may be unable to make good on its promise. Since unanimity is required to commit a transaction, the fate of T is sealed as soon as at least one site responds with abort T. Note that the coordinator site S can decide unilaterally to abort T as it is one of the sites at which T has executed. The final verdict regarding T is determined at the time the coordinator writes that verdict commit or abort to the log and forces it to stable storage. In some implementations of the 2PC protocol, a site sends an acknowledge T message to the coordinator at the end of the second phase of the protocol. When the coordinator has received the acknowledge T message from all the sites, it adds the record complete T to the log. Failure handling in 2PC. We now examine in detail how 2PC responds to various types of failures. As we shall see, one major disadvantage of the 2PC protocol is that coordinator failure may result in blocking, and a decision either to commit or to abort T may have to be postponed until CI recovers. Failure of a participating site. When a participating site SK recovers from a failure, it must examine its log to determine the fate of those transactions that were in the midst of execution when the failure occurred. Let T be one such transaction. How will SK deal with T? We consider each of the possible alternatives. The log contains a commit T record. In this case, the site executes redo T. The log contains an abort T record. In this case, the site executes undo T. The log contains a ready T record. In this case, the site must consult CI to determine the fate of T. If CI is up, it notifies SK regarding whether T committed or aborted. In the former case, it executes redo T. In the latter case, it executes undo T. If CI is down, SK must try to find out the fate of T from other sites. It does so by sending a query status T message to all its log to determine whether T has executed there and, if so, whether T committed or aborted. It then notifies S/T about this outcome. If no site has the appropriate information, that is, whether T committed or aborted, then SK can neither abort nor commit T. The decision concerning T is postponed until SK can obtain the needed information. Thus, SK must periodically resend the query status T message to the other sites. It does so until a site recovers that contains the needed information. The site at which C resides always has the needed information. The log contains no control records abort, commit, ready concerning T. The absence of control records implies that SK failed before responding to the prepare T message from CI. Since the failure of SK means that it could not have sent such a response, by our algorithm CI must have aborted T. Hence, SK must execute undo T. Failure of the coordinator. If the coordinator fails in the midst of the execution of the commit protocol for transaction T, then the participating sites must decide on the fate of T. We shall see that in certain cases, the participating sites cannot decide whether to commit or abort T, and therefore these sites must wait for the recovery of the failed coordinator. If an active site contains a commit T record in its log, then T must be committed. If an active site contains an abort T record in its log, then T must be aborted. If some active site does not contain a ready T record in its log, then the failed coordinator CI cannot have decided to commit T. We can draw this conclusion because a site that does not have a ready T record in its log cannot have sent a ready T message to Q. However, the coordinator may have decided to abort F. Rather than wait for CI to recover, it is preferable to abort T in this case. If none of the preceding cases holds, then all the active sites must have a ready T record in their logs, but no additional control records such as abort T or commit T. Since the coordinator has failed, it is impossible to determine whether a decision has been made or, if so, what that decision is until the coordinator recovers. Thus, the active sites must wait for CI to recover. As long as the fate of T remains in doubt, T may continue to hold system resources. For example, if locking is used, T may hold locks on data at active sites. Such a situation is undesirable because hours or days may pass before CI is again active. During this time, other transactions may be forced to wait for T. As a result, data are unavailable not only on the failed site CI, but on active sites as well. The amount of unavailable data increases as the downtime of CI grows. This situation is called the blocking problem because T is blocked pending the recovery of the site CI. Failure of the network. When a link fails, the messages in the process of being routed through the link do not arrive at their destinations intact. From the viewpoint of the sites connected through that link, the other sites appear to have failed. Thus, our previous schemes apply here as well. When a number of links fail, the network may partition. In this case, two possibilities exist. The coordinator and all its participants may remain in one partition. In this case, the failure has no effect on the commit protocol. Alternatively, the coordinator and its participants may belong to several partitions. In this case, messages between the participant and the coordinator are lost, reducing the case to a link failure. Concurrency control. The transaction manager of a distributed database system manages the execution of those transactions or sub-transactions that access data stored in a local state. Each such transaction may be either a local transaction, that is, a transaction that executes only at that site, or part of a global transaction, that is, a transaction that executes at several sites. Each transaction manager is responsible for maintaining a log for recovery purposes and for participating in an appropriate concurrency control scheme to coordinate the concurrent execution of the transactions executing at that site. Locking protocols. The two-phase locking protocols described in Chapter 6 can be used in a distributed environment. The only change needed is in the way the lock manager is implemented. Here we present several possible schemes. The first deals with the case where no data replication is allowed. The others apply to the more general case where data can be replicated in several sites. We assume the existence of the shared and exclusive lock modes. Non-replicated scheme. If no data are replicated in the system, then the locking schemes can be applied as follows. Each site maintains a local lock manager whose function is to administer the lock and unlock requests for those data items stored in that site. When a transaction wishes to lock data item Q at site S1, it simply sends a message to the lock manager at site S, requesting a lock in a particular lock mode. If data item Q is locked in an incompatible mode, then the request is delayed until that request can be granted. Once it has been determined that the lock request can be granted, the lock manager sends a message back to the initiator indicating that the lock request has been granted. This scheme has the advantage of simple implementation. It requires 2 message transfers for handling lock requests and 1 message transfer for handling unlock requests. However, deadlock handling is more complex. Since the lock and unlock requests are no longer made at a single site, the various deadlock handling algorithms must be modified. These modifications are discussed in the later section of this chapter. Single coordinator approach. Several concurrency control schemes can be used in systems that allow data replication. Under the single coordinator approach, the system maintains a single lock manager that resides in a single chosen site, say SI. All lock and unlock requests are made at site SI. When a transaction needs to lock a data item, it sends a lock request to SI. The lock manager determines whether the lock can be granted immediately. If so, it sends a message to that effect to the site at which the lock request was initiated. Otherwise, the request is delayed until it can be granted, and at that time a message is sent to the site at which the lock request was initiated. The transaction can read the data item from any one of the sites at which a replica of the data item resides. In the case of a write operation, all the sites where a replica of the data item resides must be involved in the writing. The scheme has the following advantages. Simple implementation. This scheme requires 2 messages for handling lock requests and 1 message for handling unlock requests. Simple deadlock handling. Since all lock and unlock requests are made at one site, the deadlock handling algorithms can be applied directly to this environment. The disadvantages of the scheme include the following. Bottleneck. The site S becomes a bottleneck since all requests must be processed there. Vulnerability. If the site S fails, the concurrency controller is lost. Either processing must stop or a recovery scheme must be used. A compromise between these advantages and disadvantages can be achieved through a multiple coordinator approach in which the lock manager function is distributed over several sites. Each lock manager administers the lock and unlock requests for a subset of the data items, and the lock managers reside in different sites. This distribution reduces the degree to which the coordinator is a bottleneck, but it complicates deadlock handling since the lock and unlock requests are not made at a single site. Majority protocol. The majority protocol is a modification of the non-replicated data scheme presented earlier. The system maintains a lock manager at each site. Each manager controls the locks for all the data or replicas of data stored at that site. When a transaction wishes to lock a data item Q that is replicated in n different sites, it must send a lock request to more than one half of the n sites in which Q is stored. Each lock manager determines whether the lock can be granted immediately as far as it is concerned. As before, the response is delayed until the request can be granted. The transaction does not operate on Q until it has successfully obtained a lock on a majority of the replicas of Chapter 18/18. The scheme deals with replicated data in a decentralized manner, thus avoiding the drawbacks of central control. However, it suffers from its own disadvantages. Implementation. The majority protocol is more complicated to implement than the previous schemes. It requires 2 brackets n divided by 2 plus 1 close brackets messages for handling lock requests and open brackets n divided by 2 plus 1 close bracket messages for handling unlock requests. Deadlock handling. Since the lock and unlock requests are not made at one site, the deadlock handling algorithms must be modified. In addition, a deadlock can occur even if only one data item is being locked. To illustrate, consider a system with 4 sites and full replication. Suppose that transactions T1 and T2 wish to lock data item Q in exclusive mode. Transaction T1 may succeed in locking Q at sites S1 and S3, while transaction 2 may succeed in locking Q at sites S2 and S4. Each then must wait to acquire the third lock, and hence a deadlock has occurred. Biased protocol. The biased protocol is similar to the majority protocol. The difference is that requests for shared locks are given more favorable treatment than are requests for exclusive locks. The system maintains a lock manager at each site. Each manager manages the locks for all the data items stored at that site. Shared and exclusive locks are handled differently. Shared locks. When a transaction needs to lock data item Q, it simply requests a lock on Q from the lock manager at one site containing a replica. Exclusive locks. When a transaction needs to lock data item Q, it requests a lock on Q from the lock manager at each site containing a replica. As before, the response to the request is delayed until the request can be granted. The scheme has the advantage of imposing less overhead on read operations than does the majority protocol. This advantage is especially significant in common cases in which the frequency of reads is much greater than the frequency of writes. However, the additional overhead on writes is a disadvantage. Furthermore, the biased protocol shares the majority protocol's disadvantage of complexity in handling deadlock. Primary copy. Yet another alternative is to choose one of the replicas as the primary copy. Thus, for each data item Q, the primary copy of Q must reside in precisely one site, which we call the primary site of Q. When a transaction needs to lock a data item Q, it requests a lock at the primary site of chapter 18/18. As before, the response to the request is delayed until the request can be granted. This scheme enables us to handle concurrency control for replicated data in much the same way as for unreplicated data. Implementation of the method is simple. However, if the primary site of Q fails, Q is inaccessible even though other sites containing a replica may be accessible. Time-stamping. The principal idea behind the time-stamping scheme is that each transaction is given a unique timestamp which is used to decide the serialization order. Our first task then, in generalizing the centralized scheme to a distributed scheme, is to develop a method for generating unique timestamps. Our previous protocols can then be applied directly to the non-replicated environment. Generation of unique timestamps. Two primary methods are used to generate unique timestamps. One is centralized and one is distributed. In the centralized scheme, a single site is chosen for distributing the timestamps. The site can use a logical counter or its own local clock for this purpose. In the distributed scheme, each site generates a local unique timestamp using either a logical counter or the local clock. The global unique timestamp is obtained by concatenation of the local unique timestamp with the site identifier, which must be unique. Figure below, generation of timestamp. The order of concatenation is important. We use the site identifier in the least significant position to ensure that the global timestamps generated in one site are not always greater than those generated in another site. Compare this technique for generating unique timestamps with the one in previous session for generating unique names. We may still have a problem if one site generates local timestamps at a faster rate than do other sites. In such a case, the fast site's logical counter will be larger than those of other sites. Therefore, all timestamps generated by the fast site will be larger than those generated by other sites. A mechanism is needed to ensure that local timestamps are generated fairly across the system. To accomplish the fair generation of timestamps, we define within each site Si a logical clock LCI which generates the local timestamp. To ensure that the various logical clocks are synchronized, we require that a site Si advance its logical clock whenever a transaction T with timestamp X, Y variables visits that site and X is greater than the current value of LCI. In this case, site Si advances its logical clock to the value X plus 1. If the system clock is used to generate timestamps, then timestamps are assigned fairly provided that no site has a system clock that runs fast or slow. Since clocks may not be perfectly accurate, a technique similar to that used for logical clocks must be used to ensure that no clock gets far ahead or far behind another clock. Timestamp ordering scheme. The basic timestamp scheme can be extended in a straightforward manner to a distributed system. As in the centralized case, cascading rollbacks may result if no mechanism is used to prevent a transaction from reading a data item value that is not yet committed. To eliminate cascading rollbacks, we can combine the basic timestamp scheme with the 2PC protocol to obtain a protocol that ensures serializability with no cascading rollbacks. We leave the development of such an algorithm to you. The basic timestamp scheme just described suffers from the undesirable property that conflicts between transactions are resolved through rollbacks rather than through waits. To alleviate this problem, we can buffer the various read and write operations, that is, delay them until a time when we are assured that these operations can take place without causing aborts. A read X operation by Ti must be delayed if there exists a transaction Tj that will perform a write X operation but has not yet done so, and Ts Tj is less than Ts Ti. Similarly, a write X operation by Ti must be delayed if there exists a transaction Ti that will perform either a read X or a write X operation, and Ts Tj is less than Ti. Various methods are available for ensuring this property. One such method, called the conservative timestamp ordering scheme, requires each site to maintain a read queue and a write queue consisting of all the read and write requests that are to be executed at the site and that must be delayed to preserve the above property. Deadlock handling. The deadlock prevention, deadlock avoidance, and deadlock detection algorithms can be extended so that they can be used in a distributed system. Deadlock prevention and avoidance. The deadlock prevention and deadlock avoidance algorithms can be used in a distributed system provided that appropriate modifications are made. For example, we can use the resource ordering deadlock prevention technique by simply defining a global ordering among the system resources. That is, all resources in the entire system are assigned unique numbers, and a process may request a resource at any processor with unique number only if it is not holding a resource with a unique number greater than I. Similarly, we can use the banker's algorithm in a distributed system by designing one of the processes in the system, the banker, as the process that maintains the information necessary to carry out the banker's algorithm. Every resource request must be channeled through the banker. The global resource ordering deadlock prevention scheme is simple to implement in a distributed environment and requires little overhead. The banker's algorithm can also be implemented easily, but it may require too much overhead. The banker may become a bottleneck since the number of messages to and from the banker may be large. Thus, the banker's scheme does not seem to be of practical use in a distributed system. We turn next to a new deadlock prevention scheme based on a timestamp ordering approach with resource preemption. Although this approach can handle any deadlock situation that may arise in a distributed system, for simplicity we consider only the case of a single instance of each resource type. To control the preemption, we assign a unique priority number to each process. These numbers are used to decide whether the process Pj should wait for a process Pi. For example, we can let Pi wait for Pj if Pj has a priority higher than that of Pi, otherwise Pi is rollback. The scheme prevents deadlocks because for every edge Pi goes to Pj in the wait for graph, Pi has a higher priority than Pj. Thus, a cycle cannot exist. One difficulty with this scheme is the possibility of starvation. Some processes with extremely low priorities may always be rollback. This difficulty can be avoided through the use of timestamps. Each process in the system is assigned a unique timestamp when it is created. Two complementary deadlock prevention schemes using timestamps have been proposed. The wait-die scheme. This approach is based on a non-preemptive technique. When process Pi requests a resource currently held by Pj, Pj is allowed to wait only if it has a smaller timestamp than does Pi, that is, Pi is older than P. Otherwise, P is rollback, dies. For example, suppose that processes P1, P2 and P3 have timestamps 5, 10 and 15 respectively. If P1 requests a resource held by P2, P1 will wait. If P3 requests a resource held by P2, P3 will be rolled back. The wound wait scheme. This approach is based on a preemptive technique and is a counterpart to the wait-die approach. When process Pi requests a resource currently held by Pj, Pi is allowed to wait only if it has a larger timestamp than does Pj. That is, Pi is younger than Pj. Otherwise, Pj is rolled back, Pj is wounded by Pi. Returning to our previous example with processes P1, P2 and P3, if P1 requests a resource held by P2, then the resource will be preempted from P1 and P2 will be rolled back. If P3 requests a resource held by P2, then P3 will wait. Both schemes can avoid starvation provided that when a process is rolled back, it is not assigned a new timestamp. Since timestamps always increase, a process that is rolled back will eventually have the smallest timestamp. Thus, it will not be rolled back again. There are, however, significant differences in the way the two schemes operate. In the wait-die scheme, an older process must wait for a younger one to release its resource. Thus, the older the process gets, the more it tends to wait. By contrast, in the wound wait scheme, an older process never waits for a younger process. In the wait-die scheme, if a process Pi dies and is rolled back because it has requested a resource held by process Pj, then Pi may reissue the same sequence of requests when it is restarted. If the resource is still held by Pj, then Pj will die again. Thus, P may die several times before acquiring the needed resource. Contrast these series of events with what happens in the wound wait scheme. Process Pi is wounded and rolled back because Pj has requested a resource it holds. When Pi is restarted and requests the resource now being held by Pj, Pi waits. Thus, fewer rollbacks occur in the wound wait scheme. The major problem with both schemes is that unnecessary rollbacks may occur. Deadlock detection. The deadlock prevention algorithm may preempt resources even if no deadlock has occurred. To prevent unnecessary preemptions, we can use a deadlock detection algorithm. We construct a wait-for graph describing the resource allocation state. Since we are assuming only a single resource of each type, a cycle in the wait-for graph represents a deadlock. The main problem in a distributed system is deciding how to maintain the wait-for graph. We illustrate this problem by describing several common techniques to deal with this issue. These schemes require each site to keep a local wait-for graph. The nodes of the graph correspond to all the processes, local as well as non-local, currently holding or requesting any of the resources local to that site. For example, in figure below, two local waits, we have a system consisting of two sites, each maintaining its local wait-for graph. Site S1, Site S2. Note that processes Pi and Pj appear in both graphs, indicating that the processes have requested resources at both sites. These local wait-for graphs are constructed in the usual manner for local processes and resources. When a process Pi in site Si needs a resource held by process Pj in site Sj, a request message is sent by Pi to site Si. The edge Pi to Pj is then inserted in the local wait-for graph of site S2. Global wait graph for the above graph. The graph that we obtain by taking the union of the two wait-for graphs of above figure does indeed contain a cycle, implying that the system is in a deadlocked state. Clearly, if any local wait-for graph has a cycle, deadlock has occurred. The fact that we find no cycles in any of the local wait for graphs does not mean that there are no deadlocks, however. To illustrate this problem, we consider the above system. Each wait for graph is acyclic. Nevertheless, a deadlock exists in the system. To prove that a deadlock has not occurred, we must show that the union of all local graphs is acyclic. A number of methods are available to organize the wait for graph in a distributed system. We describe several common schemes here. Centralized approach. In the centralized approach, a global wait for graph is constructed as the union of all the local wait for graphs. It is maintained in a single process, the deadlock detection coordinator. Since there is communication delay in the system, we must distinguish between two types of wait for graphs. The real graph describes the real but unknown state of the system at any instance in time, as would be seen by an omniscient observer. The constructed graph is an approximation generated by the coordinator during the execution of its algorithm. The constructed graph must be generated so that, whenever the detection algorithm is invoked, the reported results are correct. By correct, we mean the following. If a deadlock exists, then it is reported properly. If a deadlock is reported, then the system is indeed in a deadlocked state. As we shall show, it is not easy to construct such correct algorithms. The wait for graph may be constructed at 3 different points in time. Whenever a new edge is inserted in or removed from one of the local wait for graphs, periodically, when a number of changes have occurred in a wait for graph, whenever the deadlock detection coordinator needs to invoke the cycle detection algorithm. When the deadlock detection algorithm is invoked, the coordinator searches its global graph. If a cycle is found, a victim is selected to be rolled back. The coordinator must notify all the sites that a particular process has been selected as victim. The sites in turn roll back the victim process. Let us consider option 1. Whenever an edge is either inserted in or removed from a local graph, the local site must also send a message to the coordinator to notify it of this modification. On receiving such a message, the coordinator updates its global graph. Alternatively, option 2, a site can send a number of such changes in a single message periodically. Returning to our previous example, the coordinator process will maintain the global wait for graph as depicted in figure below. When site S2 inserts the edge P3 leads to P4 in its local wait for graph, it also sends a message to the coordinator. Similarly, when site S1 deletes the edge P5 leads to P1 because P1 has released a resource that was requested by P5, an appropriate message is sent to the coordinator. Fully distributed approach. In the fully distributed deadlock detection algorithm, all controllers share equally the responsibility for detecting deadlock. Every site constructs a wait for graph that represents a part of the total graph depending on the dynamic behavior of the system. The idea is that if a deadlock exists, a cycle will appear in at least one of the partial graphs. We present one such algorithm which involves construction of partial graphs in every site. Each site maintains its own local wait for graph. Allow wait for graph in this scheme differs from the one described earlier in that we add one additional node Px to the graph. An arc Pi leads to Px exists in the graph if Pi is waiting for a data item in another site being held by any process. Similarly, an arc Px leads to Pj exists in the graph if a process at another site is waiting to acquire a resource currently being held by Pj in this local site. Election algorithms. Many distributed algorithms employ a coordinator process that performs functions needed by the other processes in the system. These functions include enforcing mutual exclusion, maintaining a global wait-for graph for deadlock detection, replacing a lost token, and controlling an input or output device in the system. If the coordinator process fails due to the failure of the site at which it resides, the system can continue execution only by restarting a new copy of the coordinator on some other site. The algorithms that determine whether a new copy of the coordinator should be restarted are called election algorithms. Election algorithms assume that a unique priority number is associated with each active process in the system. For each of notation, we assume that the priority number of a process, Pi, is 1. To simplify our discussion, we assume a one-to-one correspondence between processes and sites and thus refer to both as processes. The coordinator is always the process with the largest priority number. Hence, when a coordinator fails, the algorithm must elect that active process with the largest priority number. This number must be sent to each active process in the system. In addition, the algorithm must provide a mechanism for a recovered process to identify the current coordinator. In this section, we present examples of election algorithms for two different configurations of distributed systems. The first algorithm applies to systems where every process can send a message to every other process in the system. The second algorithm applies to systems organized as a ring, logically or physically. Both algorithms require N2 messages for an election, where N is the number of processes in the system. We assume that a process that has failed knows on recovery that it has indeed failed and thus takes appropriate actions to rejoin the set of active processes. The bully algorithm. Suppose that process Pi sends a request that is not answered by the coordinator within a time interval t. In this situation, it is assumed that the coordinator has failed and P tries to elect itself as the new coordinator. This task is completed through the following algorithm. Process Pi sends an election message to every process with a higher priority number. Process Pi then waits for a time interval t for an answer from any one of these processes. If no response is received within time t, Pi assumes that all processes with numbers greater than I have failed and elects itself the new coordinator. Process Pi restarts a new copy of the coordinator and sends a message to inform all active processes with priority numbers less than I that Pi is the new coordinator. However, if an answer is received, Pi begins a time interval t, waiting to receive a message informing it that a process with a higher priority number has been elected. That is, some other process is electing itself coordinator and should report the results within time t. If no message is sent within t, then the process with a higher number is assumed to have failed, and process Pi should restart the algorithm. If Pi is not the coordinator, then at any time during execution, Pi may receive one of the following two messages from process Pi. Pj has a new coordinator where j is greater than I. Process Pi in turn records this information. Pj has started an election where j is less than I. Process Pi sends a response to Pj and begins its own election algorithm provided that Pi has not already initiated such an election. The process that completes its algorithm has the highest number and is elected as the coordinator. It has sent its number to all active processes with smaller numbers. After a failed process recovers, it immediately begins execution of the same algorithm. If there are no active processes with higher numbers, the recovered process forces all processes with lower numbers to let it become the coordinator process, even if there is a currently active coordinator with a lower number. For this reason, the algorithm is termed the bully algorithm. We can demonstrate the operation of the algorithm with a simple example of a system consisting of processes Pi through Pj. The operations are as follows. All processes are active. P4 is the coordinator process. P1 and P4 fail. P2 determines that P4 has failed by sending a request that is not answered within time t. P2 then begins its election algorithm by sending a request to P3. P3 receives the request, responds to P2, and begins its own algorithm by sending an election request to P4. P2 receives P3's response and begins waiting for an interval t. P4 does not respond within an interval t, so P3 elects itself the new coordinator and sends the number 3 to P2 and P1. P1 does not receive the number since it has failed. Later, when P1 recovers, it sends an election request to P2, P3 and P4. P2 and P3 respond to P1 and begin their own election algorithms. P3 will again be elected through the same events as before. Finally, P4 recovers and notifies P1, P2 and P3 that it is the current coordinator. P4 sends no election requests since it is the process with the highest number in the system. The ring algorithm. The ring algorithm assumes that the links are unidirectional and that each process sends its messages to the neighbor on the right. The main data structure used by the algorithm is the active list, a list that contains the priority numbers of all active processes in the system when the algorithm ends. Each process maintains its own active list. The algorithm works as follows. If process Pi detects a coordinator failure, it creates a new active list that is initially empty. It then sends a message, elect I, to its right neighbor and adds the number I to its active list. If Pi receives a message elect J from the process on the left, it must respond in one of three ways. If this is the first elect message it has seen or sent, Pi creates a new active list with the number I. It then sends the message elect I followed by the message elect J.S. If I is not equal to j, that is, the message received does not contain Pi's number, then Pj adds I to its active list and forwards the message to its right neighbor. If I equals to j, that is, Pi receives the message elect I, then the active list for P now contains the numbers of all the active processes in the system. Process Pi can now determine the largest number in the active list to identify the new coordinator process. This algorithm does not specify how a recovering process determines the number of the current coordinator process. One solution requires a recovering process to send an inquiry message. This message is forwarded around the ring to the current coordinator, which in turn sends a reply containing its number. Reaching agreement. For a system to be reliable, we need a mechanism that allows a set of processes to agree on a common value. Such an agreement may not take place for several reasons. First, the communication medium may be faulty, resulting in lost or garbled messages. Second, the processes themselves may be faulty, resulting in unpredictable process behavior. The best we can hope for in this case is that processes fail in a clean way, stopping their execution without deviating from their normal execution pattern. In the worst case, processes may send garbled or incorrect messages to other processes or even collaborate with other failed processes in an attempt to destroy the integrity of the system. The Byzantine generals problem provides an analogy for this situation. Several divisions of the Byzantine army, each commanded by its own general, surround an enemy camp. The Byzantine generals must reach agreement on whether or not to attack the enemy at dawn. It is crucial that all generals agree, since an attack by only some of the divisions would result in defeat. The various divisions are geographically dispersed, and the generals can communicate with one another only via messengers who run from camp to camp. The generals may not be able to reach agreement for at least two major reasons. Messengers may get caught by the enemy and thus may be unable to deliver their messages. This situation corresponds to unreliable communication in a computer system. Generals may be traitors, trying to prevent the loyal generals from reaching an agreement. This situation corresponds to faulty processes in a computer system. Unreliable communications. Let us first assume that if processes fail, they do so in a clean way and that the communication medium is unreliable. Suppose that process Pi at site Si, which has sent a message to process Pi at site S2, needs to know whether Pj has received the message so that it can decide how to proceed with its computation. For example, Pi may decide to compute a function foo if Pj has received its message, or to compute a function boo if Pj has not received the message because of some hardware failure. To detect failures, we can use a timeout scheme. When Pi sends out a message, it also specifies a time interval during which it is willing to wait for an acknowledgement message from Pi. When Pi receives the message, it immediately sends an acknowledgement to Pi. If Pi receives the acknowledgement message within the specified time interval, it can safely conclude that Pi has received its message. If, however, a timeout occurs, then Pi needs to retransmit its message and wait for an acknowledgement. This procedure continues until Pi either gets the acknowledgement message back or is notified by the system that site N is down. In the first case, it will compute Si. In the latter case, it will compute F. Note that if these are the only two viable alternatives, Pi must wait until it has been notified that one of the situations has occurred. Suppose now that Pi also needs to know that Pi has received its acknowledgement message so that it can decide how to proceed with its computation. For example, Pj may want to compute foo only if it is assumed that Pj got its acknowledgement. In other words, Pi and Pj will compute foo if and only if both have agreed on it. It turns out that in the presence of failure, it is not possible to accomplish this task. More precisely, it is not possible in a distributed environment for processes Pi and Pj to agree completely on their respective states. To prove this claim, let us suppose that a minimal sequence of message transfers exists such that after the messages have been delivered, both processes agree to compute foo. Let M be the last message sent by Pi to Pj. Since Pi does not know whether its message will arrive at Pj, since the message may be lost due to a failure, Pi will execute foo regardless of the outcome of the message delivery. Thus, M could be removed from the sequence without affecting the decision procedure. Hence, the original sequence was not minimal, contradicting our assumption and showing that there is no sequence. The process can never be sure that both will compute foo. Faulty processes. Now let us assume that the communication medium is reliable, but that processes can fail in unpredictable ways. Consider a system of n processes of which no more than m are faulty. Suppose that each process Pi has some private value of Vi. we wish to devise an algorithm that allows each non-faulty process Pi to construct a vector as follows. There are many solutions to this problem and they share the following properties. A correct algorithm can be devised only if n is greater than 3 times m plus 1. The worst case delay for reaching agreement is proportionate to m plus 1 message passing delays. The number of messages required for reaching agreement is large. No single process is trustworthy, so all processes must collect all information and make their own decisions. Rather than presenting a general solution which would be complicated, we present an algorithm for the simple case where m equals to 1 and n equals to 4. The algorithm requires 2 rounds of information exchange. Each process sends its private value to the other 3 processes. Each process sends the information it has obtained in the first round to all other processes. A faulty process obviously may refuse to send messages. In this case, a non-faulty process can choose an arbitrary value and pretend that the value was sent by the faulty process. Once these 2 rounds are completed, a non-faulty process Pi can construct its vector xi equals to ai1, ai2, ai3, ai4 as follows. Distributed file systems. A distributed file system, DFS, is a distributed implementation of the classical time-sharing model of a file system where multiple users share files and storage resources. The purpose of a DFS is to support the same kind of sharing when the files are physically dispersed among the sites of a distributed system. In this chapter, we describe how a DFS can be designed and implemented. First, we discuss common concepts on which DFSs are based. Then, we illustrate our concepts by examining one influential DFS, the Andrew File System AFS. Background. As we noted in the preceding section, a distributed system is a collection of loosely coupled computers interconnected by a communication network. These computers can share physically dispersed files by using a distributed file system, DFS. In this chapter, we use the term DFS to mean distributed file systems in general, not the commercial Transact DFS product. The latter is referred to as Transact DFS. Also, NFS refers to NFS version 3 unless otherwise noted. To explain the structure of a DFS, we need to define the terms service, server, and client. A service is a software entity running on one or more machines and providing a particular type of function to clients. A server is the service software running on a single machine. A client is a process that can invoke a service using a set of operations that form its client interface. Sometimes a lower-level interface is defined for the actual cross-machine interaction. It is the intermachine interface. Using this terminology, we say that a file system provides file services to clients. A client interface for a file service is formed by a set of primitive file operations such as create a file, delete a file, read from a file, and write to a file. The primary hardware component that a file server controls is a set of local secondary storage devices, usually magnetic disks, on which files are stored and from which they are retrieved according to the client's requests. A DFS is a file system whose clients, servers, and storage devices are dispersed among the machines of a distributed system. Accordingly, service activity has to be carried out across the network. Instead of a single centralized data repository, the system frequently has multiple and independent storage devices. As you will see in this text, the concrete configuration and implementation of a DFS may vary from system to system. In some configurations, servers run on dedicated machines. In others, a machine can be both a server and a client. A DFS can be implemented as part of a distributed operating system or, alternatively, by a software layer whose task is to manage the communication between conventional operating systems and file systems. The distinctive features of a DFS are the multiplicity and autonomy of clients and servers in the system. Ideally, a DFS should appear to its clients to be a conventional centralized file system. The multiplicity and dispersion of its servers and storage devices should be made invisible. That is, the client interface of a DFS should not distinguish between local and remote files. It is up to the DFS to locate the files and to arrange for the transport of the data. A transparent DFS facilitates user mobility by bringing the user's environment, that is, home directory, to wherever a user logs in. The most important performance measurement of a DFS is the amount of time needed to satisfy service requests. In conventional systems, this time consists of disk access time and a small amount of CPU processing time. In a DFS, however, a remote access has the additional overhead attributed to the distributed structure. This overhead includes the time to deliver the request to a server as well as the time to get the response across the network back to the client. For each direction, in addition to the transfer of the information, there is the CPU overhead of running the communication protocol software. The performance of a DFS can be viewed as another dimension of the DFS's transparency. That is, the performance of an ideal DFS would be comparable to that of a conventional file system. The fact that a DFS manages a set of dispersal storage devices is the DFS's key distinguishing feature. The overall storage space managed by a DFS is composed different and remotely located smaller storage spaces. Usually, these constituent storage spaces correspond to sets of files. A component unit is a smaller set of files that can be stored on a single machine independently from other units. All files belonging to the same component unit must reside in the same location. Distributed system structure. Introduction. A distributed system is a collection of processors that do not share memory or a clock. Instead, each processor has its own local memory, and the processors communicate with one another through communication lines such as local area or wide area networks. The processors in a distributed system vary in size and function. Such systems may include small handheld or real-time devices, personal computers, workstations, and large mainframe computer systems. A distributed file system is a file service system whose users, servers, and storage devices are dispersed among the sites of a distributed system. Accordingly, service activity has to be carried out across the network. Instead of a single centralized data repository, there are multiple independent storage devices. The benefits of a distributed system include giving users access to the resources maintained by the system and thereby speeding up computation and improving data availability and reliability because a system is distributed. However, it must provide mechanisms for process synchronization and communication, for dealing with the deadlock problem, and for handling failures that are not encountered in a centralized system. A distributed system is a collection of loosely coupled processes interconnected by a communication network. From the point of view of a specific processor in a distributed system, the rest of the processors and their respective resources are remote, whereas its own resources are local. The processes in a distributed system may vary in size and function. They may include small microprocessors, workstations, mini-computers, and large general-purpose computer systems. These processes are referred to by a number of names such as sites, nodes, computers, machines, and hosts, depending on the context in which they are mentioned. We mainly use site to indicate the location of a machine and host to refer to a specific system at a site. Generally, one host at one site, the server has a resource that another host at another site, the client or user, would like to use. A general structure of a distributed system is shown below. There are 4 major reasons for building distributed systems: resource sharing, computation speedup, reliability, communication. Resource sharing. If a number of different sites with different capabilities are connected to one another, then a user at one site may be able to use the resources available at another. For example, a user at site A may be using a laser printer located at site B. Meanwhile, a user at B may access a file that resides at A. In general, resource sharing in a distributed system provides mechanisms for sharing files at remote sites, processing information in a distributed database, printing files at remote sites, using remote specialized hardware devices such as a high-speed array processor, and performing other operations. Computation speedup. If a particular computation can be partitioned into sub-computations that can run concurrently, then a distributed system allows us to distribute the sub-computations among the various sites. The sub-computations can be run concurrently and thus provide computation speedup. In addition, if a particular site is currently overloaded with jobs, some of them can be moved to other lightly loaded sites. This movement of jobs is called load sharing. Automated load sharing, in which the distributed operating system automatically moves jobs, is not yet common in commercial systems. Reliability. If one site fails in a distributed system, the remaining sites can continue operating, giving the system better reliability. If the system is composed of multiple large autonomous installations, that is, general-purpose computers, the failure of one of them should not affect the rest. If, however, the system is composed of small machines, each of which is responsible for some crucial system function, such as terminal character input-output or the file system, then a single failure may halt the operation of the whole system. In general, with enough redundancy in both hardware and data, the system can continue operation even if some of its sites have failed. The failure of a site must be detected by the system and appropriate action may be needed to recover from the failure. The system must no longer use the services of that site. In addition, if the function of the failed site can be taken over by another site, the system must ensure that the transfer function occurs correctly. Finally, when the failed site recovers or is repaired, mechanisms must be available to integrate it back into the system smoothly. Communication. When several sites are connected to one another by a communication network, users at the various sites have the opportunity to exchange information. At a low level, messages are passed between systems, much as messages are passed between processes in the single computer message system. Given message passing, all the higher-level functionality found in standalone systems can be expanded to encompass the distributed system. Such functions include file transfer, login, mail, and remote procedure calls, RPCs. The advantage of a distributed system is that these functions can be carried out over great distances. Two people at geographically distant sites can collaborate on a project, for example, by transferring the files of the project, logging into each other's remote systems to run programs, and exchanging mail to coordinate the work. Users minimize the limitations inherent in long-distance work. The advantages of distributed systems have resulted in an industry-wide trend toward downsizing. Many companies are replacing their mainframes with networks of workstations or personal computers. Companies get a bigger bang for the buck, that is, better functionality for the cost, more flexibility in locating resources and expanding facilities, better user interfaces, and easier maintenance. File replication. Replication of files on different machines in a distributed file system is a useful redundancy for improving availability. Multi-machine replication can benefit performance too. Selecting a nearby replica to serve an access request results in shorter surface time. NFS v4. Our coverage of NFS thus far has only considered version 3 or v3 NFS. The most recent NFS standard is version 4 v4, and it differs fundamentally from previous versions. The most significant change is that the protocol is now state-field, meaning that the server maintains the state of the client session from the time the remote file is opened until it is closed. Thus, the NFS protocol now provides open function and close function operations. Previous versions of NFS, which are stateless, provide no such operations. Furthermore, previous versions specify separate protocols for mounting remote file systems and for locking remote files. v4 provides all of these features under a single protocol. In particular, the mount protocol was eliminated, allowing NFS to work with network firewalls. The mount protocol was a notorious security hole in NFS implementations. Additionally, v4 has enhanced the ability of clients to cache file data locally. This feature improves the performance of the distributed file system as clients are able to resolve more file accesses from the local cache rather than having to go through the server. v4 allows clients to request file locks from servers as well. If the server grants the request, the client maintains the lock until it is released or its lease expires. Clients are also permitted to renew existing leases. Traditionally, Unix-based systems provide advisory file locking, whereas Windows operating systems use mandatory locking. To allow NFS to work well with non-Unix systems, v4 now provides mandatory locking as well. The new locking and caching mechanisms are based on the concept of delegation, whereby the server delegates responsibilities for a file's lock and contents to the client that requested the lock. That delegated client maintains in cache the current version of the file, and other clients can ask that delegated client for lock access and file contents until the delegated client relinquishes the lock and delegation. Finally, whereas previous versions of NFS are based on the UDP network protocol, v4 is based on TCP, which allows it to better adjust to varying traffic loads on the network. Delegating these responsibilities to clients reduces the load on the server and improves cache coherency. The basic requirement of a replication scheme is that different replicas of the same file reside on failure-independent machines. That is, the availability of one replica is not affected by the availability of the rest of the replicas. This obvious requirement implies that replication management is inherently a location-opaque activity. Provisions for placing a replica on a particular machine must be available. It is desirable to hide the details of replication from users. Mapping a replicated file name to a particular replica is the task of the naming scheme. The existence of replicas should be invisible to higher levels. At lower levels, however, the replicas must be distinguished from one another by different lower-level names. Another transparency requirement is providing replication control at higher levels. Replication control includes determination of the degree of replication and of the placement of replicas. Under certain circumstances, we may want to expose these details to users. Locus, for instance, provides users and system administrators with mechanisms to control the replication scheme. The main problem associated with replicas is updating. From a user's point of view, replicas of a file denote the same logical entity, and thus an update to any replica must be reflected on all other replicas. More precisely, the relevant consistency semantics must be preserved when accesses to replicas are viewed as virtual accesses to the replica's logical files. If consistency is not a primary importance, it can be sacrificed for availability and performance. In this fundamental trade-off in the area of fault tolerance, the choice is between preserving consistency at all costs, thereby creating a potential for indefinite blocking, and sacrificing consistency under some, we hope rare, circumstances of catastrophic failures for the sake of guaranteed progress. Locus, for example, employs replication extensively and sacrifices consistency in the case of network partition for the sake of availability of files for read and write accesses. IBIS uses a variation of the primary copy approach. The domain of the name mapping is a pair, primary replica identifier, local replica identifier. If no local replica exists, a special value is used. Thus, the mapping is relative to a machine. If the local replica is the primary one, the pair contains two identical identifiers. IBIS supports demand replication and automatic replication control policy similar to whole file caching. Under demand replication, reading of a non-local replica causes it to be cached locally, thereby generating a new non-primary replica. Updates are performed only on the primary copy and cause all other replicas to be invalidated through the sending of appropriate messages. Atomic and serialized invalidation of all non-primary replicas is not guaranteed. Hence, a stale replica may be considered valid. To satisfy remote write accesses, we migrate the primary copy to the requesting machine. Naming and transparency. Naming is a mapping between logical and physical objects. For instance, users deal with logical data objects represented by file names, whereas the system manipulates physical blocks of data stored on disk tracks. Usually, a user refers to a file by a textual name. The latter is mapped to a lower-level numerical identifier that in turn is mapped to disk blocks. This multi-level mapping provides users with an abstraction of a file that hides the details of how and where on the disk the file is stored. In transparent DFS, a new dimension is added to the abstraction, that of hiding where in the network the file is located. In a conventional file system, the range of the naming mapping is an address within a disk. In a DFS, this range is expanded to include the specific machine on whose disk the file is stored. Going one step further with the concept of treating files as abstractions leads to the possibility of file replication. Given a file name, the mapping returns a set of the locations of this file replicas. In this abstraction, both the existence of multiple copies and their locations are hidden. Naming structures. We need to differentiate two related notions regarding name mappings in a DFS. Location transparency. The name of a file does not reveal any hint of the file's physical storage location. Location independence. The name of a file does not need to be changed when the file's physical storage location changes. Both definitions are relative to the level of naming discussed previously, since files have different names at different levels. A location-independent naming scheme is a dynamic mapping, since it can map the same file name to different locations at two different times. Therefore, location independence is a stronger property than is location transparency. In practice, most of the current DFSs provide a static, location-transparent mapping for user-level names. These systems, however, do not support file migration, that is, changing the location of a file automatically is impossible. Hence, the notion of location independence is irrelevant for these systems. Files are associated permanently with a specific set of disk blocks. Files and disks can be moved between machines manually, but file migration implies an automatic operating system-initiated action. Only AFS and a few experimental file systems support location independence and file mobility. AFS supports file mobility mainly for administrative purposes. A protocol provides migration of AFS component units to satisfy high-level user requests without changing either the user-level names or the low-level names of the corresponding files. A few aspects can further differentiate location independence and static location transparency. Divorce of data from location, as exhibited by location independence, provides a better abstraction for files. A file name should denote the file's most significant attributes, which are its contents rather than its location. Location-independent files can be viewed as logical data containers that are not attached to a specific storage location. If only static location transparency is supported, the file name still denotes a specific, although hidden, set of physical disk blocks. Static location transparency provides users with a convenient way to share data. Users can share remote files by simply naming the files in a location-transparent manner as though the files were local. Nevertheless, sharing the storage space is cumbersome because logical names are still statically attached to physical storage devices. Location independence promotes sharing the storage space itself as well as the data objects. When files can be mobilized, the overall system-wide storage space looks like a single virtual resource. A possible benefit of such a view is the ability to balance the utilization of disks across the system. Location independence separates the naming hierarchy from the storage devices hierarchy and from the intercomputer structure. By contrast, if static location transparency is used, although names are transparent, we can easily expose the correspondence between component units and machines. The machines are configured in a pattern similar to the naming structure. This configuration may restrict the architecture of the system unnecessarily and conflict with other considerations. A server in charge of a root directory is an example of a structure that is dictated by the naming hierarchy and contradicts decentralization guidelines. Once the separation of name and location has been completed, clients can access files residing on remote server systems. In fact, these clients may be diskless and rely on servers to provide all files including the operating system kernel. Special protocols are needed for the boot sequence, however. Consider the problem of getting the kernel to a diskless workstation. The diskless workstation has no kernel, so it cannot use the DFS code to retrieve the kernel. Instead, a special boot protocol stored in read-only memory ROM on the client is invoked. It enables networking and retrieves only one special file, the kernel or boot code, from a fixed location. Once the kernel is copied over the network and loaded, its DFS makes all the other operating system files available. The advantages of diskless clients are many, including lower cost because the client machines require no disks, and greater convenience when an operating system upgrade occurs, only the server needs to be modified. The disadvantages are the added complexity of the boot protocols and the performance loss resulting from the use of a network rather than a local disk. The current trend is for clients to use both local disks and remote file servers. Operating systems and networking software are stored locally. The file systems containing user data and possibly applications are stored on remote file systems. Some client systems may store commonly used applications such as word processors and web browsers on the local file system as well. Other, less commonly used applications may be pushed from the remote file server to the client on demand. The main reason for providing clients with local file systems rather than pure diskless systems is that disk drives are rapidly increasing in capacity and decreasing in cost, with new generations appearing every year or so. The same cannot be said for networks, which evolve every few years. Overall, systems are growing more quickly than our networks, so extra work is needed to limit network access to improve system throughput. Naming schemes. There are three main approaches to naming scheme in a DFS. In the simplest approach, a file is identified by some combination of its host name and local name, which guarantees a unique system-wide name. In this, for instance, a file is identified uniquely by the name host:/local name, where local name is a UMX-like path. This naming scheme is neither location transparent nor location independent. Nevertheless, the same file operations can be used for both local and remote files. The DFS is structured as a collection of isolated component units, each of which is an entire conventional file system. In this first approach, component units remain isolated, although means are provided to refer to a remote file. We do not consider this scheme any further in this text. The second approach was popularized by Sun's network file system, NFS. NFS is the file system component of ONC+, a networking package supported by many Unix vendors. NFS provides a means to attach remote directories to local directories, thus giving the appearance of a coherent directory tree. Early NFS versions allowed only previously mounted remote directories to be accessed transparently. With the advent of the automount feature, mounts are done on demand based on a table of mount points and file structure names. Components are integrated to support transparent sharing, although this integration is limited and is not uniform because each machine may attach different remote directories to its tree. The resulting structure is versatile. We can achieve total integration of the component file systems by using the third approach. A single global name structure spans all the files in the system. Ideally, the composed file system structure is isomorphic to the structure of the conventional file system. In practice, however, the many special files, for example, Unix device files and machine-specific binary directories, make this goal difficult to attain. To evaluate naming structures, we look at their administrative complexity. The most complex and most difficult to maintain structure is the NFS structure because any remote directory can be attached anywhere onto the local directory tree. The resulting hierarchy can be highly unstructured. If a server becomes unavailable, some arbitrary set of directories on different machines becomes unavailable. In addition, a separate accreditation mechanism controls which machine is allowed to attach which directory to its tree. Thus, a user might be able to access a remote directory tree on one client but be denied access on another client. Implementation techniques. Implementation of transparent naming requires a provision for the mapping of a file name to the associated location. To keep this mapping manageable, we must aggregate sets of files into component units and provide the mapping on a component unit basis rather than on a single file basis. This aggregation serves administrative purposes as well. Unix-like systems use the hierarchical directory tree to provide name-to-location mapping and to aggregate files recursively into directories. To enhance the availability of the crucial mapping information, we can use replication, local, caching, or both. As we noted, local independence means that the mapping changes over time. Hence, replicating the mapping makes a simple yet consistent update of this information impossible. A technique to overcome this obstacle is to introduce low-level location-independent file identifiers. Textual file names are mapped to lower-level file identifiers that indicate to which component unit the file belongs. These identifiers are still location-independent. They can be replicated and cached freely without being invalidated by migration of component units. The inevitable price is the need for a second level of mapping which maps component units to locations and needs a simple yet consistent update mechanism. Implementing Unix-like directory trees using these low-level location-independent identifiers makes the whole hierarchy invariant under component unit migration. The only aspect that does change is the component unit location mapping. A common way to implement low-level identifiers is to use structured names. These names are bit strings that usually have two parts. The first part identifies the component unit to which the file belongs. The second part identifies the particular file within the unit. Variants with more parts are possible. The invariant of structured names, however, is that individual parts of the name are unique at all times only within the context of the rest of the parts. We can obtain uniqueness at all times by taking care not to reuse a name that is still used by adding sufficiently more bits. This method is used in AFS, or by using a timestamp as one part of the name as done in Apollo domain. Another way to view this process is that we are taking a location-transparent system such as IBIS and adding another level of abstraction to produce a location-independent naming scheme. Aggregating files into component units and using lower-level location-independent file identifiers are techniques exemplified in AFS. Network operating systems. In this section, we describe the two general categories of network-oriented operating systems: network operating systems, distributed operating systems. Network operating systems. Network operating systems are simpler to implement but generally more difficult for users to access and utilize than are distributed operating systems, which provide more features. A network operating system provides an environment in which users who are aware of the multiplicity of machines can access remote resources by either logging in to the appropriate remote machine or transferring data from the remote machine to their own machines. We come across the following in network operating system: remote login, remote file transfer. Remote login. An important function of a network operating system is to allow users to log in remotely. The Internet provides the Telnet facility for this purpose. To illustrate this facility, let's suppose that a user at Westminster College wishes to compute on cs.yale.edu, a computer that is located at Yale University. To do so, the user must have a valid account on that machine. To log in remotely, the user issues the command telnet cs.yale.edu. This command results in the formation of a socket connection between the local machine at Westminster College and the cs.yale.edu computer. After this connection has been established, the networking software creates a transparent bidirectional link so that all characters entered by the user are sent to a process on cs.yale.edu and all the output from that process is sent back to the user. The process on the remote machine asks the user for a login name and a password. Once the correct information has been received, the process acts as a proxy for the user 1 who can compute on the remote machine just as any local user can. Remote file transfer. Another major function of a network operating system is to provide a mechanism for remote file transfer from one machine to another. In such an environment, each computer maintains its own local file system. If a user at one site, say cs.uvm.edu, wants to access a file located on another computer, say cs.yale.edu, then the file must be copied explicitly from the computer at Yale to the computer at the University of Vermont. The Internet provides a mechanism for such a transfer with the File Transfer Protocol (FTP) program. Suppose that a user on cs.uvm.edu wants to copy a Java program server.java that resides on cs.yale.edu. The user must first invoke the FTP program by executing ftpcs.yale.edu. The program then asks the user for a login name and a password. Once the correct information has been received, the user must connect to the subdirectory where the file server.java resides and then copy the file by executing getserver.java. In this scheme, the file location is not transparent to the user. Users must know exactly where each file is. Moreover, when there is no real file sharing, because a user can only copy a file from one site to another. Thus, several copies of the same file may exist, resulting in a waste of space. In addition, if these copies are modified, the various copies will be inconsistent. Notice that, in our example, the user at the University of Vermont must have login permission on cs.yale.edu. PTP also provides a way to allow a user who does not have an account on the Yale computer to copy files remotely. This remote copying is accomplished through the anonymous FTP method, which works as follows. The file to be copied, that is server.java, must be placed in a special subdirectory, say JTP, with the protection set to allow the public to read the file. A user who wishes to copy the file uses the FTP command as before. When the user is asked for the login name, the user supplies the name anonymous and an arbitrary password. Once anonymous login is accomplished, care must be taken by the system to ensure that this partially authorized user does not access inappropriate files. Generally, the user is allowed to access only those files that are in the directory tree of user anonymous. Any files placed here are accessible to any anonymous users subject to the usual file protection scheme used on that machine. Anonymous users, however, cannot access files outside of this directory tree. Implementation of the FTP mechanism is similar to Telnet implementation. A daemon on the remote site watches for requests to correlate to the system's PTP port. Login authentication is accomplished and the user is allowed to execute commands remotely. Unlike the Telnet daemon, which executes any command for the user, the PTP daemon responds only to a predefined set of file-related commands. These include the following: get transfer, a file from the remote machine to the local machine; put, transfer from the local machine to the remote machine; ls or dir, list files in the current directory on the remote machine; cd, change the current directory on the remote machine. There are also various commands to change transfer modes for binary or ASCII files and to determine connection status. An important point about Telnet and PTP is that they require the user to change paradigms. PTP requires the user to know a command set entirely different from the normal operating system commands. Telnet requires a smaller shift. The user must know appropriate commands on the remote system. For instance, a user on a Windows machine who telnets to a Unix machine must switch to Unix commands for the duration of the telnet session. Facilities are more convenient for users if they do not require the use of a different set of commands. Distributed operating systems are designed to address this problem. Distributed operating systems. In a distributed operating system, users access remote resources in the same way they access local resources. Data and process migration from one site to another is under the control of the distributed operating system. We come across the following in distributed operating system: data migration, computation migration, process migration. Data migration. Suppose a user on site A wants to access data such as a file that resides at site B. The system can transfer the data by one of two basic methods. One approach to data migration is to transfer the entire file to site A. From that point on, all access to the file is local. When the user no longer needs access to the file, a copy of the file, if it has been modified, is sent back to site B. Even if only a modest change has been made to a large file, all the data must be transferred. This mechanism can be thought of as an automated FTP system. This approach was used in the Andrew file system, but it was found to be too inefficient. The other approach is to transfer to site A only those portions of the file that are actually necessary for the immediate task. If another portion is required later, another transfer will take place. When the user no longer wants to access the file, any part of it that has been modified must be sent back to site B. The Sun Microsystems Network File System (NFS) protocol uses this method, as do newer versions of Andrew. The Microsoft SMB protocol, running on top of either TCP/IP or the Microsoft NetBEUI protocol, also allows file sharing over a network. Clearly, if only a small part of a large file is being accessed, the latter approach is preferable. If significant portions of the file are being accessed, however, it is more efficient to copy the entire file. In both methods, data migration includes more than the mere transfer of data from one site to another. The system must also perform various data translations if the two sites involved are not directly compatible, for instance, if they use different character code representations or represent integers with a different number or order of bits. Computer migration. In some circumstances, we may want to transfer the computation rather than the data across the system. This approach is called computation migration. For example, consider a job that needs to access various large files that reside at different sites to obtain a summary of those files. It would be more efficient to access the files at the sites where they reside and return the desired results to the site that initiated the computation. Generally, if the time to transfer the data is longer than the time to execute the remote command should be used. Such a computation can be carried out in different ways. Suppose that process P wants to access a file at site A. Access to the file is carried out at site A and could be initiated by an RPC. An RPC uses a datagram protocol, UDP, on the Internet to execute a routine on a remote system. Process P invokes a predefined procedure at site A. The procedure executes appropriately and then returns the result to P. Alternatively, process P can send a message to site A. The operating system at site A then creates a new process Q whose function is to carry out the designated task. When process Q completes its execution, it sends the needed result back to P via the message system. In this scheme, process P may execute concurrently with the process Q. In fact, it may have several processes running concurrently on several sites. Either method could be used to access several files residing at various sites. One RPC might result in the invocation of another RPC or even in the transfer of messages to another site. Similarly, process Q could, during the course of its execution, send a message to another site which in turn would create another process. This process might either send a message back to Q or repeat the cycle. Process migration. A local extension of computation migration is process migration. When a process is submitted for execution, it is not always executed at the site at which it is initiated. The entire process or parts of it may be executed at different sites. This scheme may be used for several reasons. Load balancing. The processes or sub-processes may be distributed across the network to even the workload. Computation speed-up. If a single process can be divided into a number of sub-processes that can run concurrently on different sites, then the total process turnaround time can be reduced. Hardware preference. The process may have characteristics that make it more suitable for execution on some specialized processor, such as matrix inversion on any array processor, rather than on a microprocessor. Software preference. The process may require software that is available at only a particular site, and either the software cannot be moved or it is less expensive to move the process. Data access. Just as in computation migration, if the data being used in the computation are numerous, it may be more efficient to have a process run remotely than to transfer all the data. We use two complementary techniques to move processes in a computer network. In the first, the system can attempt to hide the fact that the process has migrated from the client. The scheme has the advantage that the user does not need to code her program explicitly to accomplish the migration. This method is usually employed for achieving load balancing and computation speed-up among homogeneous systems, as they do not need user input to help them execute programs remotely. The other approach is to allow or require the user to specify explicitly how the process should migrate. This method is usually employed when the process must be moved to satisfy a hardware or software preference. Certainly, it provides data migration between a web server and a web client. It also provides computation migration. For instance, a web client could trigger a database operation on a web server. Finally, with Java, it provides a form of process migration. Java applets are sent from the server to the client where they are executed. A network operating system provides most of these features, but a distributed operating system makes them seamless and easily accessible. The result is a powerful and easy-to-use facility, one of the reasons for the huge growth of the World Wide Web. Network structure topology. Network structure. It includes the following details: topology, network types, communication, design strategies. Network topology. The sites in a distributed system can be connected physically in a variety of ways. Each configuration has advantages and disadvantages. We can compare the configurations by using the following criteria: installation cost, the cost of physically linking the sites in the system; communication cost, the cost in time and money to send a message from site A to site B; availability, the extent to which data can be accessed despite the failure of some links or sites; The various topologies are depicted in figure graphs whose nodes correspond to sites. Topology. Explanation for the above diagram. An edge from node A to node B corresponds to a direct communication link between the two sites. In a fully connected network, each site is directly connected to every other site. However, the number of links grows as the square of the number of sites, resulting in a huge installation cost. Therefore, fully connected networks are impractical in any large system. In a partially connected network, direct links exist between some but not all pairs of sites. Hence, the installation cost of such a configuration is lower than that of the fully connected network. However, if two sites A and B are not directly connected, messages from one to the other must be through a sequence of communication links. This requirement results in a higher communication cost. If a communication link fails, a message that would have been transmitted across the link must be rerouted. In some cases, another route through the network may be found so that the messages are able to reach their destination. In other cases, a failure may mean that no connection exists between some pair or pairs of sites. When a system is split into two or more unconnected subsystems, it is partitioned. Under this definition, a subsystem or partition may consist of a single node. These types have different failure characteristics and installation and communication costs. Installation and communication costs are relatively low for a tree-structured network. However, the failure of a single link in such a network can result in the networks becoming partitioned. In a ring network, at least two links must fail for partition to occur. Thus, the ring network has a higher degree of availability than does a tree-structured network. However, the communication cost is high since a message may have to cross a large number of links. In a star network, the failure of a single link results in a network partition, but one of the partitions has only a single site. Such a partition can be treated as a single site failure. The star network also has a low communication cost since each site is at most 2 links away from every other site. However, if the central site fails, all the sites in the system become disconnected from one another. Network types. There are basically 2 types of networks: local area networks, wide area networks. The main difference between the two is the way in which they are geographically distributed. Local area networks are composed of processes distributed over small areas such as a single building or a number of adjacent buildings, whereas wide area networks are composed of a number of autonomous processes distributed over a large area such as the United States. These differences imply major variations in the speed and reliability of the communications networks, and they are reflected in the distributed operating system design. Local area networks. Local area networks emerged in the early 1970s as a substitute for large mainframe computer systems. For many enterprises, it is more economical to have a number of small computers, each with its own self-contained applications, than to have a single large system, because each small computer is likely to need a full complement of peripheral devices such as disks and printers. And because some form of data sharing is likely to occur in a single enterprise, it was a natural step to connect these small systems into a network. LANs, as mentioned, are usually designed to cover a small geographical area such as a single building or a few adjacent buildings, and are generally used in an office environment. All the sites in such systems are close to one another, so the communication links tend to have a higher speed and low error rate than do their counterparts in wide area networks. High-quality, expensive cables are needed to attain this higher speed and reliability. It is also possible to use the cable exclusively for data network traffic. Over longer distances, the cost of using high-quality cable is enormous, and the exclusive use of the cable tends to be prohibitively expensive. The most common links in a local area network are twisted pair and fiber optic cabling. The most common configurations are multi-access bus, ring, and star networks. Communication speeds range from 1 megabyte per second for networks such as AppleTalk, Infrared, and the new Bluetooth local radio network to 1 gigabyte per second for Gigabit Ethernet. 10 megabits per second is the speed of 10 base T Ethernet. 100 base T Ethernet requires a higher quality cable but runs at 100 gigabits per second and is common. Also growing is the use of optical fiber-based FDDI networking. The FDDI network is token-based and runs at over 100 megabits per second. A typical LAN may consist of a number of different computers, from mainframes to laptops or PDAs, various shared peripheral devices such as laser printers and magnetic tape drives, and one or more gateways, specialized processors that provide access to other networks. An Ethernet scheme is commonly used to construct LANs. An Ethernet network has no central controller because it is a multi-access bus, so new hosts can be added easily to the network. The Ethernet protocol is defined by the IEEE 802.3 standard. There has been significant growth in using the wireless spectrum for designing local area networks. Wireless or Wi-Fi networks allow constructing a network using only a wireless router for transmitting signals between hosts. Each host has a wireless adapter networking card which allows it to join and use the wireless network. However, where Ethernet systems often run at 100 megabits per second, Wi-Fi networks typically run at slower speeds. Wide area networks. Wide area networks emerged in the late 1960s mainly as an academic research project to provide efficient communication among sites, allowing hardware and software to be shared conveniently and economically by a wide community of users. The first WAN to be designed and developed was the ARPANET. Begun in 1968, the ARPANET has grown from a 4-site experimental network to a worldwide network of networks. The Internet, comprising millions of computer systems, because the sites in a WAN are physically distributed over a large geographical area, the communication links are by default relatively slow and unreliable. Typical links are telephone lines, leased, dedicated data lines, microwave links, and satellite channels. These communication links are controlled by special communication processors which are responsible for defining the interface through which the sites communicate over the network, as well as for transferring information among the various sites. For example, the Internet WAN enables hosts at geographically separated sites to communicate with one another. The host computers typically differ from one another in type, speed, word length, operating system, and so on. Hosts are generally on LANs, which are in turn connected to the Internet via regional networks. The regional networks, such as NSFNet in the Northeast United States, are interlinked with routers to form the worldwide network. Connections between networks frequently use a telephone system service called T1, which provides a transfer rate of 1.544 megabits per second over leased line. For sites requiring faster Internet access, T1s are collected into multiple T1 units that work in parallel to provide more throughput. For instance, a T3 is composed of 28 T1 connections and has a transfer rate of 45 megabits per second. The routers control the path each message takes through the net. This routing may be either dynamic to increase communication efficiency or static to reduce security risks or to allow communication charges to be computed. Other WANs use standard telephone lines as their primary means of communication. Modems are devices that accept digital data from the computer side and convert it to the analog signals that the telephone system uses. A modem at the destination side converts the analog signal back to digital form and the destination receives the data. The Unix News Network, the UUCP, allows systems to communicate with each other at predetermined times via modems to exchange messages. The messages are then routed to other nearby systems and in this way either are propagated to all hosts on the network, public messages, or are transferred to specific destinations, private messages. WANs are generally slower than LANs. Their transmission rates range from 1200 bits per second to over 1 megabit per second. UUCP has been superseded by PPP, the point-to-point protocol. PPP functions over modem Coryu1 elections, allowing home computers to be fully connected to the Internet. Communication structures. Now that we have discussed the physical aspects of networking, we turn to the internal workings. The designer of a communication network must address 5 basic issues: naming and name resolution. How do two processes locate each other to communicate? Routing strategies. How are messages sent through the network? Packet strategies. Are packets sent individually or as a sequence? Connection strategies. How do two processes send a sequence of messages? Contention. How do we resolve conflicting demands for the network's use, given that it is a shared resource? In the following sections, we elaborate on each of these issues. Naming and name resolution. The first component of network communication is the naming of the systems in the network. For a process at site A to exchange information with process at site B, each must be able to specify the other. Within a computer system, each process has a process identifier and messages may be addressed with the process identifier. Because networked systems share no memory, however, a host within the system initially has no knowledge about the processes on other hosts. To solve this problem, processes on remote systems are generally identified by the pair host name identifier, where host name is a name unique within the network and identifier may be a process identifier or other unique number within that host. A host name is usually an alphanumeric identifier rather than a number to make it easier for users to specify. For instance, site A might have host name Homer, Marge, Bart, and Lisa. Bart is certainly easier to remember than is 12814831100. Names are convenient for humans to use, but computers prefer numbers for speed and simplicity. For this reason, there must be a mechanism to resolve the host name into a host ID that describes the destination system to the networking hardware. This mechanism is similar to the name-to-address binding that occurs during program compilation, linking, loading, and execution. In the case of host names, 2 possibilities exist. First, every host may have a data file containing the names and addresses of all the other hosts reachable on the network, similar to the binding at compile time. The problem with this model is that adding or removing a host from the network requires updating the data files on all the hosts. The alternative is to distribute the information among systems on the network. The network must then use a protocol to distribute and retrieve the information. This scheme is like execution time binding. DNS specifies the naming structure of the hosts as well as name-to-address resolution. Hosts on the Internet are logically addressed with a multi-part name. Names progress from the most specific to the most general part of the address with periods separating the fields. For instance, a bob.cs.brown.edu refers to host Bob in the Department of Computer Science at Brown University within the domain edu. Other top-level domains include .com for commercial sites and .org for organizations, as well as a domain for each country connected to the network for systems specified by country rather than organization type. Generally, the system resolves addresses by examining the host name components in reverse order. Each component has a name server, simply a process on a system that accepts a name and returns the address of the name server responsible for that name. As the final step, the name server for the host in question is contacted and a host ID is returned. For our example system, bob.cs.brown.edu, the following steps will be taken as a result of a request made by a process on system A to communicate with bob.cs.brown.edu. The kernel of system A issues a request to the name server for the edu domain, asking for the address of the name server for brown.edu would result in the following steps. The name server for the edu domain must be at a known address so that it can be queried. The edit name server returns the address of the host on which the brown.edu name server resides. The kernel on system A then queries the name server at this address and asks about cs.brown.edu. An address is returned and a request to that address for bob.cs.brown.edu now finally returns an internet address host ID for that host, for example 128.148.3L100. This protocol may seem inefficient, but local caches are usually kept at each name server to speed the process. For example, the edu name server would have been brown.edu in its cache and would inform system A that it could resolve two portions of the name, returning a pointer to the cs.brown.edu name server. Of course, the contents of these caches must be refreshed over time in case the name server is moved or its address changes. In fact, this service is so important that many optimizations have occurred in the protocol as well as many safeguards. Consider what would happen if the primary edu name server crashed. It is possible that no edu hosts would be able to have their addresses resolved, making them all unreachable. The solution is to use secondary backup name servers that duplicate the contents of the primary servers. Before the domain name service was introduced, all hosts on the internet needed to have copies of a file that contained the names and addresses of each host on the network. All changes to this file had to be registered at one site, host SRI-NIC, and periodically all hosts had to copy the updated file from SRI-NIC to be able to contact new systems or find hosts whose addresses had changed. Under the domain name service, each name server site is responsible for updating the host information for that domain. For instance, any host changes at Brown University are the responsibility of the name server for brown.edu and do not have to be reported anywhere else. DNS lookups will automatically retrieve the updated information because brown.edu is contacted directly. Within domains, there can be autonomous subdomains to distribute further the responsibility for host name and host ID changes. Java provides the necessary API to design a program that maps IP names to IP addresses. The program shown below is passed an IP name, such as bob.cs.brown.edu on the command line and either outputs the IP address of the host or returns a message indicating that the host name could not be resolved. Java program illustrating a DNS lookup. Explanation about the above program. An INET address is a Java class representing an IP name or address. The static method getByName function belonging to the INET address class is passed a string representation of an IP name and it returns the corresponding INET address. The program then invokes the getHostAddress function method, which internally uses DNS to look up the IP address of the designated host. Generally, the operating system is responsible for accepting from its process a message destined for host name identifier and for transferring that message to the appropriate host. The kernel on the destination host is then responsible for transferring the message to the process named by the identifier. This exchange is by no means trivial. Routing strategies. When a process at site A wants to communicate with a process at site B, how is the message sent? If there is only one physical path from A to B, such as in a star or tree-structured network, the message must be sent through the path. However, if there are multiple physical paths from A to B, then several routing options exist. Each site has a routing table indicating the alternative paths that can be used to send a message to other sites. The table may include information about the speed and cost of the various communication paths, and it may be updated as necessary either manually or via programs that exchange routing information. The three most common routing schemes are fixed routing, dynamic routing, virtual routing. Fixed routing. A path from A to B is specified in advance and does not change unless a hardware failure disables it. Fixed routing cannot adapt to link failures or load changes. In other words, if a path has been established between A and B, the messages must be sent along this path even if the path is down or is used more heavily than another possible path. We can partially remedy this problem by using virtual routing and can avoid it completely by using dynamic routing. Usually, the shortest path is chosen so that communication costs are minimized. Virtual routing. A path from A to B is fixed for the duration of one. Different sessions involving messages from A to B may use different paths. A session could be as short as a file transfer or as long as a remote login period. Dynamic routing. The path used to send a message from site A to site B is chosen only when the message is sent because the decision is made dynamically. Separate messages may be assigned different paths. Site A will make a decision to send the message to site C. C in turn will decide to send it to site D, and so on. Eventually, a site will deliver the message to B. Usually, a site sends a message to another site on whatever link is the least used at that particular time. There are trade-offs among these three schemes. Fixed routine and virtual routing ensure that messages from A to B will be delivered in the order in which they were sent. In dynamic routing, messages may arrive out of order. We can remedy this problem by appending a sequence number to each message. Dynamic routing is the most complicated to set up and run. However, it is the best way to manage routing in complicated environments. Unix provides both fixed routing for use on hosts within simple networks and dynamic routing for complicated network environments. It is also possible to mix the two. Within a site, the host may just need to know how to reach the system that connects the local network to other networks, such as company-wide networks or the Internet. Such a node is known as a gateway. Each individual host has a static route to the gateway, although the gateway itself uses dynamic routing to reach any host on the rest of the network. A router is the entity within the computer network responsible for routing messages. A router can be a host computer with routing software or a special-purpose device. Either way, a router must have at least two network connections or else it would have nowhere to route messages. A router decides whether any given message needs to be passed from the network on which it is received to any other network connected to the router. It makes this determination by examining the destination internet address of the message. The router checks its tables to determine the locations of the destination host, or at least of the network to which it will send the message toward the destination host. In the case of static routing, this table is changed only by manual update. A new file is loaded onto the router. With dynamic routing, a routing protocol is used between routers to inform them of network changes and to allow them to update their routing tables automatically. Gateways and routers typically are dedicated hardware devices that run code out of firmware. Packet strategies. Messages are generally of variable length. To simplify the system design, we commonly implement communication with fixed-length messages called packets, frames, or datagrams. A communication implemented in one packet can be sent to its destination in a connectionless message. A connectionless message can be unreliable, in which case the sender has no guarantee that and cannot tell whether the packet reached its destination. Alternatively, the packet can be reliable. Usually, in this case, a packet is returned from the destination indicating that the packet arrived. Of course, the return packet could be lost along the way. If a message is too long to fit within one packet, or if the packets need to flow back and forth between the two communicators, a connection is established to allow the reliable exchange of multiple packets. Connection strategies. Once messages are able to reach their destinations, processes can institute communications sessions to exchange information. Pairs of processes that want to communicate over the network can be connected in a number of ways. The three most common schemes are circuit switching, message switching, packet switching. Circuit switching. If two processes want to communicate, a permanent physical link is established between them. This link is allocated for the duration of the communication session, and no other process can use that link during this period, even if the two processes are not actively communicating for a while. This scheme is similar to that used in the telephone system. Once a communication line has been opened between two parties, that is, party A calls party B, no one else can use the circuit until the communication is terminated explicitly, for example, when the parties hang up. Message switching. If two processes want to communicate, a temporary link is established for the duration of one message transfer. Physical links are allocated dynamically among correspondents as needed and are allocated for only short periods. Each message is a block of data with system information such as the source, the destination, and error correction codes (ECC) that allows the communication network to deliver message to the destination correctly. The scheme is similar to the post office mailing system. Each letter is a message that contains both the destination address and source return address. Many messages from different users can be shipped over the same link. Packet switching. One logical message may have to be divided into a number of packets. Each packet may be sent to its destination separately, and each therefore must include a source and destination address with its data. Furthermore, the various packets may take different paths through the network. The packets must be reassembled into messages as they arrive. Note that it is not harmful for data to be broken into packets, possibly routed separately and reassembled at the destination. Breaking up an audio signal, say a telephone communication, in contrast, could cause great confusion if it was not done carefully. There are obvious trade-offs among these schemes. Circuit switching requires substantial setup time and may waste network bandwidth, but it incurs less overhead for shipping each message. Conversely, message and packet switching require less setup time but incur more overhead per message. Also, In packet switching, each message must be divided into packets and later reassembled. Packet switching is the method most commonly used on data networks because it makes the best use of network bandwidth. Contention. Depending on the network topology, a link may connect more than two sites in the computer network, and several of these sites may want to transmit information over a link simultaneously. This situation occurs mainly in a ring or multi-access bus network. In this case, the transmitted information may become scrambled. If it does, it must be discarded, and the sites must be notified about the problem so that they can retransmit the information. If no special provisions are made, the situation may be repeated, resulting in degraded performance. Several techniques have been developed to avoid repeated collisions, including collision detection and token passing. CSMA-CD. Before transmitting a message over a link, a site must listen to determine whether another message is currently being transmitted over that link. This technique is called Carrier Sense with Multiple Access, CSMA. If the link is free, the site can start transmitting. Otherwise, it must wait and continue to listen until the link is free. If two or more sites begin transmitting at exactly the same time, each thinking that no other site is using the link, then they will register a collision detection CD and will stop transmitting. Each site will try again after some random time interval. The main problem with this approach is that when the system is very busy, many collisions may occur and thus performance may be degraded. Nevertheless, CSMA-CD has been used successfully in the Ethernet system, the most common local area network system. One strategy for limiting the number of collisions is to limit the number of hosts per Ethernet network. Adding more hosts to a congested network could result in poor network throughput. As systems get faster, they are able to send more packets per time segment. As a result, the number of systems per Ethernet network generally is decreasing, so that networking performance is kept reasonable. Token passing. A unique message type known as a token continuously circulates in the system, usually a ring structure. A site that wants to transmit information must wait until the token arrives. It removes the token from the ring and begins to transmit its messages. When the site completes its round of messages passing, it retransmits the token. This action, in turn, allows another site to receive and remove the token and to start its message transmission. If the token gets lost, the system must then detect the loss and generate a new token. It usually does that by declaring an election to choose a unique site where a new token will be generated. Design strategies. The purpose of the analysis phase is to figure out what the business needs. The purpose of the design phase is to figure out how to provide it. The steps in both analysis and design phases are highly interrelated and may require much going back and forth. The system architecture design consists of plans for the hardware, software, communications, security, and global support for the new application. The designers must decide if processing will occur in the server-based, at the personal computer, client-based, or in some combination of these, client-server-based. The network model shows major components of the system, where they are located and how they will be connected to one another. The hardware and software specifications describe these components in detail and aid those responsible for purchase and acquisition of these products. Functions of the application system: data storage, data access logic, application logic, presentation logic. Remote file access. Consider a user who requests access to a remote file. The server storing the file has been located by the naming scheme, and now the actual data transfer must take place. One way to achieve this transfer is through a remote service mechanism whereby requests for accesses are delivered to the server machine performs the accesses, and the results are forwarded back to the user. One of the most common ways of implementing remote service is the Remote Procedure Call (RPC) paradigm. A direct analogy exists between disk access methods in conventional file systems and the remote service method in a DFS. Using the remote service method is analogous to performing a disk access for each access request. To ensure reasonable performance of a remote service mechanism, we can use a form of caching. In conventional file systems, the rationale for caching is to reduce disk input-output, thereby increasing performance, whereas in DFS, the goal is to reduce both network traffic and disk input-output. In the following discussion, we describe the implementation of caching in a DFS and contrast it with the basic remote service paradigm. Basic caching scheme. The concept of caching is simple. If the data needed to satisfy the access request are not already cached, then a copy of those data is brought from the server to the client system. Accesses are performed on the cached copy. The idea is to retain recently accessed disk blocks in the cache so that repeated accesses to the same information can be handled locally without additional network traffic. A replacement policy, for example, least recently used, keeps the cache size bounded. No direct correspondence exists between accesses and traffic to the server. Files are still identified with one master copy residing at the server machine, but copies or parts of the file are scattered in different caches. When a cached copy is modified, the changes need to be reflected on the master copy to preserve the relevant consistency semantics. The problem of keeping the cached copies consistent with the master file is the cache consistency problem. DFS caching could just as easily be called network virtual memory. It acts similarly to demand-paged virtual memory, except that the backing store usually is not a local disk but rather a remote server. NFS allows the swap space to be mounted remotely, so it actually can implement virtual memory over a network, notwithstanding the resulting performance penalty. The granularity of the cache data in a DFS can vary from blocks of a file to an entire file. Usually more data are cached than are needed to satisfy a single access, so that many accesses can be served by the cached data. This procedure is much like the disk read-ahead. AFS caches files in large chunks 64 KB. The other systems discussed in this chapter support caching of individual blocks driven by client demand. Increasing the caching unit increases the hit ratio, but it also increases the miss penalty because each miss requires more data to be transferred. It increases the potential for consistency problems as well. Selecting the unit of caching involves considering parameters such as the network transfer unit and the RPC protocol service unit if an RPC protocol is used. The network transfer unit for Ethernet, a packet, is about 1.5 KB, so larger units of cached data need to be disassembled for delivery and reassembled on reception. Block size and total cache size are obviously of importance for block caching schemes. In Unix-like systems, common block sizes are 4 KB and 8 KB. For large caches over 1 MB, large block sizes over 8 KB are beneficial. For smaller caches, large block sizes are less beneficial because they result in fewer blocks in the cache and a lower hit ratio. Cache location. Where should the cached data be stored? On disk or in main memory? Disk cache have one clear advantage over main memory caches. They are reliable. Modifications to cache data are lost in a crash if the cache is kept in volatile memory. Moreover, if the cached data are kept on disk, they are still there during recovery and there is no need to fetch them again. Main memory caches have several advantages of their own, however. Main memory caches permit workstations to be diskless. Data can be accessed more quickly from a cache in main memory than from one on a disk. Technology is moving toward larger and less expensive memory. The achieved performance speed-up is predicted to outweigh the advantages of disk caches. The server caches used to speed up disk input-output will be in main memory regardless of where user caches are located. If we use main memory caches on the user machine too, we can build a single caching mechanism for use by both servers and users. Many remote access implementations can be thought of as hybrids of caching and remote service. In NFS, for instance, the implementation is based on remote service but is augmented with client and server-side memory caching for performance. Similarly, Sprite's implementation is based on caching, but under certain circumstances, a remote service method is adopted. Thus, to evaluate the two methods, we must evaluate to what degree either method is emphasized. The NFS protocol and most implementations do not provide disk caching. Once the NFS client reads blocks of a file from the server, it caches them in memory as well as on disk. If the memory copy is flushed or even if the system reboots, the disk cache is referenced. If a needed block is neither in memory nor in the cache's disk cache, an RPC is sent to the server to retrieve the block, and the block is written into the disk cache as well as stored in the memory cache for client use. Cache update policy. The policy used to write modified data blocks back to the server's master copy has a critical effect on the system's performance and reliability. The simplest policy is to write data through to disk as soon as they are placed in any cache. The advantage of a write-through policy is reliability. Little information is lost when a client system crashes. However, this policy requires each write access to wait until the information is sent to the server, so it causes poor write performance. Caching with write-through is equivalent to using remote service for write accesses and exploiting caching only for read accesses. An alternative is the delayed write policy, also known as write-back caching, where we delay updates to the master copy. Modifications are returned to the cache and then are written through to the server at a later time. This policy has two advantages over write-through. First, because writes are made to the cache, write accesses complete much more quickly. Second, data may be overwritten before they are written back, in which case only the last update needs to be written at all. Unfortunately, delayed write schemes introduce reliability problems since unwritten data are lost whenever a user machine crashes. Variations of the delayed write policy differ in when modified data blocks are flushed to the server. One alternative is to flush a block when it is about to be ejected from the client's cache. This option can result in good performance, but some blocks can reside in the client's cache a long time before they are written back to the server. A compromise between this alternative and the write-through policy is to scan the cache at regular intervals and to flush blocks that have been modified since the most recent scan, just as Unix scans its local cache. Sprite uses this policy with a 30-second interval, and NFS uses the policy for file data, but once a write is issued to the server during a cache flush, the write must reach the server's disk before it is considered complete. NFS treats metadata, directory data, and file attribute data differently. Any metadata changes are issued synchronously to the server. Thus, file structure loss and directory structure corruption are avoided when a client or the server crashes. Cache and its use of caching. For NFS with cache, writes are also written to the local disk cache area when they are written to the server to keep all copies consistent. Thus, NFS with cache improves performance over standing NFS on a read request with a cache hit, but decreases performance for read or write requests with a cache miss. As with all caches, it is vital to have a high cache hit rate to gain performance. Yet another variation on delayed write is to write data back to the server when the file is closed. This write-on-close policy is used in AFS. In the case of files that are open for short periods or are modified rarely, this policy does not significantly reduce network traffic. In addition, the write-on-close policy requires the closing process to delay while the file is written through, which reduces the performance advantages of delayed writes. For files that are open for long periods and are modified frequently, however, the performance advantages of this policy over delayed write with more frequent flushing are apparent. Consistency. A client machine is faced with the problem of deciding whether or not a locally cached copy of the data is consistent with the master copy and hence can be used. If the client machine determines that its cached data are out of date, accesses can no longer be served by those cached data. An up-to-date copy of the data needs to be cached. There are two approaches to verifying the validity of cached data. Client-initiated approach. The client initiates a validity check in which it contacts the server and checks whether the local data are consistent with the master copy. The frequency of the validity checking is the crux of this approach and determines the resulting consistency semantics. It can range from a check before every access to a check only on first access to a file on file open, basically. Every access coupled with a validity check is delayed compared with an access served immediately by the cache. Alternatively, checks can be initiated at fixed time intervals. Depending on its frequency, the validity check can load both the network and the server. Server-initiated approach. The server records for each client the files or parts of files that it caches. When the server detects a potential inconsistency, it must react. A potential for inconsistency occurs when two different clients in conflicting modes cache a file. If Unix semantics is implemented, we can resolve the potential inconsistency by having the server play an active role. The server must be notified whenever a file is opened, and the intended mode, read or write, must be indicated for every open. The server can then act when it detects that file has been opened simultaneously in conflicting modes by disabling caching for that particular file. Actually disabling caching results in switching to a remote service mode of operation. A comparison of caching and remote service. Essentially, the choice between caching and remote service trades off potentially increased performance with decreased simplicity. We evaluate this trade-off by listing the advantages and disadvantages of the two methods. When caching is used, the local cache can handle a substantial number of the remote accesses efficiently. Capitalizing on locality in file access patterns makes caching even more attractive. Thus, most of the remote accesses will be served as fast as will local ones. Moreover, servers are contacted only occasionally rather than for each access. Consequently, server load and network traffic are reduced and the potential for scalability is enhanced. By contrast, when the remote service method is used, every remote access is handled across the network. The penalty in network traffic, server load, and performance is obvious. Total network overhead is lower for transmitting big chunks of data, as is done in caching, than for transmitting series of responses to specific requests, as in the remote service method. Furthermore, disk access routines on the server may be better optimized if it is known that requests will always be for large, contiguous segments of data rather than for random disk blocks. The cache consistency problem is the major drawback of caching. When access patterns exhibit infrequent writes, caching is superior. However, when writes are frequent, the mechanisms employed to overcome the consistency problem incur substantial overhead in terms of performance, network traffic, and server load. So that caching will confer a benefit, execution should be carried out on machines that have either local disks or large main memories. Remote access on diskless, small memory capacity machines should be done through the remote service method. In caching, since data are transferred en masse between the server and the client rather than in response to the specific needs of a file operation, the lower-level inter-machine interface is different from the upper-level user interface. The remote service paradigm, in contrast, is just an extension of the local file system interface across the network. Thus, the inter-machine interface mirrors the user interface. Remote services. Remote service mechanism requests for accesses that are delivered to the server. The server machine performs the accesses and the results are forwarded back to the user. One of the most common ways of implementing remote service is the Remote Procedure Call (RPC) paradigm. A direct analogy exists between disk access methods in conventional file systems and the remote service method in a DFS. Using the remote service method is analogous to performing a disk access for each access request. Remote procedure calls (RPCs) are executed via message RPC function, which sends a message and waits for exactly one return message from the sender. In this way, the RPC models a typical subroutine procedure call but can work between systems, hence the term remote. Robustness. A distributed system may suffer from various types of hardware failure. The failure of a link, the failure of a site, and the loss of a message are the most common types. To ensure that the system is robust, we must detect any of these failures, reconfigure the system so that computation can continue, and recover when a site or a link is repaired. We come across the following in robustness: failure detection, reconfiguration, recovery from failure, fault tolerance. Failure detection. In an environment with no shared memory, we are generally unable to differentiate among link failure, site failure, and message loss. We can usually detect only that one of these failures has occurred. Once a failure has been detected, appropriate action must be taken. What action is appropriate depends on the particular application. To detect link and site failure, we use a handshaking procedure. Suppose that sites A and B have a direct physical link between them. At fixed intervals, the sites send each other an "I am up" message. If site A does not receive this message within a predetermined time period, it can assume that site B has failed, that the link between A and B has failed, or that the message from B has been lost. At this point, site A has two choices. It can wait for another time period to receive an "I am up" message from B, or it can send an "Are you up" message to B. If time goes by and site A still has not received an "I am up" message, or if site A has sent an "Are you up" message and has not received a reply, the procedure can be repeated. Again, the only conclusion that Site A can draw safely is that some type of failure has occurred. Site A can try to differentiate between link failure and site failure by sending an "Are you up?" message to B by another route if one exists. If and when B receives this message, it immediately replies positively. This positive reply tells A that B is up and that the failure is in the direct link between them. Since we do not know in advance how long it will take the message to travel from A to B and back, we must use a timeout scheme. At the time A sends the "Are you up?" message, it specifies a time interval during which it is willing to wait for the reply from B. If A receives the reply message within that time interval, then it can safely conclude that B is up. If not, however, that is, if a timeout occurs, then A may conclude only that one or more of the following situations has occurred. Site B is down. The direct link, if one exists, from A to B is down. The alternative path from A to B is down. The message has been lost. Site A cannot, however, determine which of these events has occurred. Reconfiguration. Suppose that Site A has discovered through the mechanism described in the previous section that a failure has occurred. It must then initiate a procedure that will allow the system to reconfigure and to continue its normal mode of operation. If a direct link from A to B has failed, this information must be broadcast to every site in the system so that the various routing tables can be updated accordingly. If the system believes that a site has failed because that site can be reached no longer, then all sites in the system must be so notified so that they will no longer attempt to use the services of the failed site. The failure of a site that serves as a central coordinator for some activity, such as deadlock detection, requires the election of a new coordinator. Similarly, if the failed site is part of a logical ring, then a new logical ring must be constructed. Note that if the site has not failed, that is, if it is up but cannot be reached, then we may have the undesirable situation in which two sites serve as the coordinator. When the network is partitioned, the two coordinators, each for its own partition, may initiate conflicting actions. For example, if the coordinators are responsible for implementing mutual exclusion, we may have a situation in which two processes are executing simultaneously in their critical sections. Recovery from failure. When a failed link or site is repaired, it must be integrated into the system gracefully and smoothly. Suppose that a link between A and B has failed. When it is repaired, both A and B must be notified. We accomplish this notification by continuously repeating the handshaking procedure. Suppose that B has failed. When it recovers, it must notify all other sites that it is up again. Site B then may have to receive information from the other sites to update its local tables. For example, it may need routing table information, a list of sites that are down, or undelivered messages and mail. If the site has not failed but simply could not be reached, then this information is still required. Fault tolerance. A distributed system must tolerate a certain level of failure and continue to function normally when faced with various types of failures. Making a facility fault tolerant starts at the protocol level, as described above, but continues through all aspects of the system. We use the term fault tolerance in a broad sense. Communication faults, machine failures of all fail-stop, where the machine stops before performing an erroneous operation that is visible to other processes, storage device crashes, and decays of storage media should all be tolerated to some extent. A fault tolerance system should continue to function, perhaps in a degraded form, when faced with such failures. The degradation can be in performance, in functionality, or in both. It should be proportional, however, to the failures that caused it. A system that grinds to a halt when only one of its components fails is certainly not fault-tolerant. Unfortunately, fault tolerance can be difficult and expensive to implement. At the network layer, multiple redundant communication paths and network devices such as switches and routers are needed to avoid a communication failure. A storage failure can cause loss of the operating system, applications, or data. Storage units can include redundant hardware components that automatically take over from each other in case of a failure. In addition, RAID systems can ensure continued access to the data even in the event of one or more disk failures. A system failure without redundancy can cause an application or an entire facility to stop operation. The most simple system failure involves a system running only stateless applications. These applications can be restarted without compromising the operation so long as the applications can run on more than one computer node. Operation can continue. Such a facility is commonly known as a compute cluster because it is computation-centric. In contrast, data-centric systems involve running applications that access and modify shared data. As a result, data-centric computing facilities are more difficult to make fault-tolerant. They require failure monitoring software and special infrastructure. For instance, high availability clusters such as Veritas Cluster and Sun Cluster include 2 or more computers and a set of shared disks. Any given application can be stored on the computers or on the shared disk, but the data must be stored on the shared disk. The running applications node has exclusive access to the application's data on disk. The application is monitored by the cluster software, and if it fails, it is automatically restarted. If it cannot be restarted, or if the entire computer fails, the node's exclusive access to the application's data is terminated and is granted to another node in the cluster. The application is restarted on that new node. The application loses whatever state information was in the failed system's memory, but can continue based on whatever state it last wrote to the shared disk. From a user's point of view, a service was interrupted and then restarted, possibly with some data missing. Specific applications may improve on this functionality by implementing lock management along with clustering. With lock management, the application can run on multiple nodes and can use the same data on shared disks concurrently. Clustered databases frequently implement this functionality. If a node fails, transactions can continue on other nodes and users notice no interruption of service as long as the client is able to automatically locate the other nodes in the cluster. Any non-committed transactions on the failed node are lost, but again, client applications can be designed to retry non-committed transactions if they detect a failure of their database node. Stateful versus stateless service. There are 2 approaches for storing server-side information when a client accesses remote files. Either the server tracks each file being accessed by each client, or it simply provides blocks as they are requested by the client without knowledge of how those blocks are used. In the former case, the service provided is stateful. In the latter case, it is stateless. The typical scenario of a stateful file service is as follows. A client must perform an open function operation on a file before accessing that file. The server fetches information about the file from its disk, stores it in memory, and gives the client a connection identifier that is unique to the client and the open file. In Unix terms, the server fetches the mode and gives the client a file descriptor which serves as an index to an in-core table of inodes. This identifier is used for subsequent accesses until the session ends. A stateful service is characterized as a connection between the client and the server during a session. Either on closing the file or by a garbage collection mechanism, the server must reclaim the main memory space used by the clients that are no longer active. The key point regarding fault tolerance in a stateful service approach is that the server keeps main memory information about its clients. AFS is a stateful file service. A stateless file service avoids state information by making each request self-contained. That is, each request identifies the file and the position in the file for read and write accesses in full. The server does not need to keep a table of open files in main memory, although it usually does so for efficiency reasons. Moreover, there is no need to establish and terminate a connection through open function and close function operations. They are totally redundant since each file operation stands on its own and is not considered part of a session. A client process would open a file, and that open would not result in the sending of a remote message. Reads and writes would take place as remote messages or cache lookups. The final close by the client would again result in only a local operation. NFS is a stateless file service. The advantage of a stateful over a stateless service is increased performance. File information is cached in main memory and can be accessed easily via the connection identifier, thereby saving disk accesses. In addition, a stateful server knows whether a file is open for sequential access and can therefore read ahead the next blocks. Stateless servers cannot do so since they have no knowledge of the purpose of the client's requests. The distinction between stateful and stateless service becomes more evident when we consider the effects of a crash that occurs during a service activity. A stateful server loses all its volatile state in a crash. Ensuring the graceful recovery of such a server involves restoring the state, usually by a recovery protocol based on a dialogue with clients. Less graceful recovery requires that the operations that were underway when the crash occurred be aborted. A different problem is caused by client failures. The server needs to become aware of such failures so that it can reclaim space allocated to record the state of crashed client processes. This phenomenon is sometimes referred to as orphan detection and elimination. A stateless computer server avoids these problems since a newly reincarnated server can respond to a self-contained request without any difficulty. Therefore, the effects of server failures and recovery are almost unnoticeable. There is no difference between a slow server and a recovering server from a client's point of view. The client keeps retransmitting its request if it receives no response. The penalty for using the robust stateless service is no longer request messages and slower processing of requests, since there is no in-core information to speed the processing. In addition, stateless service imposes additional constraints on the design of the DFS. First, since each request identifies the target file, a uniform system-wide low-level naming scheme should be used. Translating remote to local names for each request would cause even slower processing of the requests. Second, since clients retransmit requests for file operations, these operations must be idempotent, that is, each operation must have the same effect and return the same output if executed several times consecutively. Self-contained read and write accesses are idempotent as long as they use an absolute byte count to indicate the position within the file they access and do not rely on an incremental offset as done in Unix read function and write function system calls. However, we must be careful when implementing destructive operations such as deleting a file to make them idempotent too. In some environments, a stateful service is a necessity. If the server employs the server-initiated method for cache validation, it cannot provide stateless service since it maintains a record of which files are cached by which clients. The way Unix uses the file descriptors and implicit offsets is inherently stateful. Servers must maintain tables to map the file descriptors to inodes and must store the current offset within a file. This requirement is why NFS, which employs a stateless service, does not use file descriptors and does include an explicit offset in every access. Conclusion. In this chapter, we have covered the following in detail: network structures, distributed system structures, distributed file systems, distributed coordination.